Right now, inside the massive server farms powering models like ChatGPT, words are not being processed like, clean, sterile logic in a calculator.
Right, definitely not.
You type a question, and you expect a perfectly ordered filing cabinet to just pull the right files and hand you an answer. But mathematically speaking, the words in your prompt are actually acting like a chaotic swarm of microscopic particles.
It's wild to think about.
They're trapped on the surface of an invisible, multidimensional sphere, just violently pulling at each other, colliding, vibrating, until they either freeze into a coherent thought or they just shatter into a complete hallucination. And today, we are looking at the math that actually proves this.
It's really a complete paradigm shift for anyone who thinks of computers as just zeros and ones. I mean, we are having to move away from thinking about artificial intelligence as just code.
Right.
We have to start looking at it through the lens of thermodynamics and fluid dynamics.
And that is exactly the mission for this deep dive. We have a paper on the desk today that is, frankly, pretty intimidating.
Oh, absolutely.
It's a cutting-edge piece of mathematics. It's titled Phase Transitions for the Noisy Transformer Model in Arbitrary Dimension. And it's by Kyunghoo and Matthew Rosenzweig. If you were to look at the paper right now, it looks like an alien language,
Yeah, it's dense.
packed with equations that govern how transformer models, which is, the architecture behind almost all modern AI, how they actually operate at a foundational level.
And it is an incredibly rigorous mathematical proof. They aren't just observing how an AI behaves, right? They are proving the fundamental physical laws of how information interacts inside the model's layers.
But hey, if you're listening, don't let the heavy math scare you off.
Yeah.
Because over the course of this deep dive, we're going to strip away the academic jargon.
Definitely.
We're going to figure out what a noisy transformer actually is. We're going to explore this invisible, high-stakes tug-of-war happening inside the AI between the gravity of human meaning and, well, the random chaos of digital noise.
Which is fascinating.
And most importantly, for you listening, we're going to explain why understanding this tug-of-war is just a game-changing leap for the future of technology. So, okay, let's unpack this. I want to start by just figuring out how a word you type on your keyboard becomes a physical particle in this model. The paper focuses on the unnormalized self-attention mechanism.
Right.
They abbreviate it as USA.
Yeah, so self-attention is really the engine of modern AI. I mean, before transformers came along, older AI models read text linearly.
Like one word after another.
Exactly, like a human reading a book. But self-attention allows the model to look at every single piece of a sentence simultaneously and figure out which pieces actually matter to each other.
Okay, so if I type a prompt, how does it physically get into this system?
Well, the first step is tokenization. The AI breaks your sentence down into tokens, which are just words or fragments of words.
Right.
Then it assigns a mathematical vector to each token. Imagine a massive spreadsheet. For every token, the AI has a list of numbers that define what that token means based on its training.
I want to make sure we can visualize this. If you are listening to this right now, just imagine a 3D graph, like the kind you drew in high school geometry. An X, Y, and Z axis.
Focused analogy.
If a token only had 3 numbers associated with it, you could plot it as a single point floating in that 3D space.
Exactly. The list of numbers is literally just a coordinate. So the word apple becomes a specific point in space. The word tree becomes another point. The word car is way over in a completely different section of the graph.
Okay, that makes sense.
But in a real AI, we aren't using 3 numbers. We are using hundreds or thousands of numbers for a single token.
Oh, wow. So we are dealing with a space that has thousands of dimensions. I mean, I can't even picture that, but I get the concept. We have coordinates. But the paper doesn't just say they're floating static in space. It says these tokens are acting like an interacting particle system. So how do coordinates interact?
Well, what's fascinating here is that this is where the self-attention mechanism actually kicks in. In the deep processing layers of the AI, these tokens are not static at all. The mathematical formula for unnormalized self-attention basically calculates how similar these coordinates are to one another.
Right?
And if they share contexts like apple and tree, the math literally creates an attractive force between them.
Like gravity.
Very much like gravity. The tokens act as physical particles and they begin to pull on each other based on their similarities. They are trying to move closer together in this mathematical space to form a cluster of meaning.
Okay, let me pause you there just to be sure I have it. If I write a sentence about baking an apple pie, I have tokens for apple, crust, cinnamon, oven, maybe kitchen. Because they are all related to baking, This attention gravity starts dragging them toward each other.
Correct. The system inherently wants to cluster related concepts so it can synthesize them and, figure out what the next word should be.
But if they're just pulling on each other, wouldn't they eventually just crash? Like, if gravity is the only force, all those words would just slam into a single dense point?
Yes, exactly.
Apple and oven and cinnamon would just become one indistinguishable mush of baking concepts.
And if that happened, the AI would lose all nuance. It wouldn't be able to distinguish between the ingredient and the appliance, which is exactly why the paper introduces the second major force in the system, the noise.
Okay.
Specifically, they refer to it as isotropic Brownian noise.
Okay, I have to stop on that phrase. Isotropic Brownian noise. That sounds like something you use to shield a warp core on Star Trek. What does that actually mean in the context of a language model?
I know, it's a mouthful, but it's actually a concept borrowed from biology and physics. Have you ever seen dust motes dancing randomly in a shaft of sunlight?
Yeah, they sort of just jitter around chaotically.
Right. That is Brownian motion. It was first observed by a botanist named Robert Brown in the 1800s when he was looking at pollen grains in water. The pollen was constantly vibrating because invisible water molecules were randomly crashing into it from all sides.
Oh, okay.
And isotropic just means this random crashing happens equally in every direction.
But there is no water inside ChatGPT, so where is this random jitter coming from?
Well, in the context of a neural network, this noise is introduced as a mathematical model for two things. Conceptually, it represents the unresolved variability and just the sheer friction of information moving through incredibly deep, complex layers of computation.
Okay, so just system static.
Exactly. Data gets processed, and there's a bit of uncertainty. But practically, engineers actually rely on this noise as a regularizer.
A regularizer, meaning it keeps things regulated.
Yes, it prevents the exact collapse you just described earlier. While the attention mechanism is acting like gravity, trying to pull all those baking words into a single point, the noise is acting as a repulsive, scattering force. It vibrates the tokens violently, pushing them apart.
I think I need an analogy here, something we can picture without having to hold thousand-dimensional geometry in our heads.
Yeah.
So imagine you, the listener, are at a massive networking event in a giant room.
Okay, I like this.
The attention mechanism is the gravity of shared interests. If you're into vintage cars and you overhear someone talking about a 1969 Mustang, you naturally drift toward them. People start forming these tight little huddles based on their similarities. That is the gravity pulling tokens together.
Right, the system is actively trying to organize the information into these huddles.
But the noise is the environment of the party itself. It's the deafening music pumping through the speakers. It's the waiters barging through the crowd with trays of drinks. It's the random people bumping into you.
Yeah.
That chaos is constantly jostling your little group, making people take a step back, maybe get distracted, and just spread out.
That captures the dynamic perfectly. You have this constant high-stakes tension. The shared interests are pulling people into distinct, meaningful clusters, but the loud, chaotic environment is constantly shaking those groups up.
Right.
It prevents the entire party from just collapsing into one giant, sweaty mob in the dead center of the room. It forces the system to maintain a spread, preserving the diversity of the tokens.
Okay, but there is a specific detail in the paper that makes my cocktail party analogy fall apart.
Oh.
Yeah, the paper says this entire tug of war, the gravity and the noise is happening on the surface of a unit sphere. They write it out as s to the power of d minus 1. Why a sphere? If we just have coordinates floating in space, why aren't they just interacting in a giant open void?
Right. That constraint actually comes from a very common, very necessary practice in machine learning called layer normalization.
Why is it necessary?
So when a neural network is processing these vectors, multiplying them, adding them up over dozens or hundreds of layers, the numbers can get wildly unstable. Some vectors might grow to massive numbers, while others shrink down to tiny decimals.
That sounds chaotic.
It is. If you let that happen, the math just blows up and the model breaks. So to keep everything stable, engineers apply layer normalization.
How does that put them on a sphere, though?
Mathematically, normalization takes every single token's coordinate vector and divides it by its own length.
I'm going to need you to walk me through the geometry of that. If you are dividing a coordinate by its length, what happens visually?
Imagine your 3D graph again. You have a point that is, say, 10 units away from the center. If you divide its coordinates by 10, its new distance from the center is exactly 1.
Oh, I see.
Now imagine a point that is only 0.5 units away from the center. If you divide its coordinates by 0.5, it stretches out. Its new distance from the center is also exactly 1.
So no matter where a token is in this infinite space, layer normalization drags it straight inward or pushes it straight outward until it's exactly a distance of 1 from the center point.
Precisely. And if you have thousands of points, and you force every single one of them to be exactly a distance of 1 from the center, what shape have you just drawn?
A sphere.
Ah!
You've just plastered every single token onto the crust of a perfectly round globe.
Yes. The entire vocabulary of the prompt is projected onto the surface of a unit sphere, and they cannot leave that surface. By the time the attention gravity starts pulling them and the Brownian noise starts jittering them, they are completely trapped on this spherical crust.
Wow.
They can slide along the curve, they can clump together, they can spread out, but they are absolutely bound to that geometry.
That is a wild image to hold in your head. So inside ChatGPT, as you watch the text generate on your screen, you can imagine thousands of these glowing points trapped on a globe. And they are desperately trying to drag themselves into tight, meaningful clusters, while the background static of the network is violently vibrating them, trying to blast them evenly across the entire surface of the sphere.
That is exactly the physical system that Munn and Rosenzweig are analyzing.
Which brings us to the most important question: who wins the tug of war? Because eventually, the AI has to make a decision and output a word. It has to settle on an arrangement. And the paper tackles this by searching for a phase transition.
Yes, and this is where the paper stops being computer science and really becomes pure statistical mechanics. They are looking for the McKeown-Vlasov free energy minimum.
McKeown-Vlasov free energy. Let me guess. Free energy doesn't mean a perpetual motion machine in this case?
What is free energy in this context?
Right, no perpetual motion. In physics, every system in nature is trying to find its lowest possible energy state. A ball at the top of a hill has potential energy, so it rolls to the bottom to minimize it.
Hot coffee has thermal energy, so it cools down to match the room. Free energy is basically a mathematical way of measuring the total stress or frustration in a system, and the McKeown-Vlasov equation specifically balances two competing sources of that stress.
And what are the two sources?
The first is relative entropy. You can think of entropy as the chaos caused by the noise. High entropy means the tokens are perfectly uniformly spread out across the entire sphere.
So in that case, the noise wins. Complete chaos, total even spread.
Exactly. The second source is the interaction energy. This is the stress caused by the attention mechanism. It represents how badly the tokens want to clump together based on their similarities.
So then the gravity wins.
Right. The free energy minimum is the exact mathematical sweet spot where these two opposing forces find a compromise. It is the state where the overall stress of the system is as low as it can possibly get.
Okay, so the system is constantly hunting for balance. But you use the phrase phase transition. When I hear phase transition, I think of boiling water turning into steam, or liquid water freezing into ice. It implies a sudden, fundamental change in the state of matter. How did that apply to words on a sphere?
It applies perfectly. The authors are looking for the exact tipping point where the balance of power shifts. They want to know the precise moment when the noise is no longer strong enough to keep the tokens spread out, and the attention gravity takes over, causing that uniform even spread to fundamentally break down into distinct clusters.
Wow.
That breakdown, that is the phase transition.
To understand how they find this tipping point, we need to look at the two parameters the paper identifies. They act kind of like volume dials on the whole system. The first dial is K.
Yes, K represents the coupling strength. You can think of it as the inverse of the noise strength.
The inverse. Okay, so if K is really high, what does that mean for our tokens?
If K is high, it means the noise is very weak. The tokens are relatively unbothered by random vibrations, so they are free to couple together. If K is low, the noise is deafening. The tokens are being violently scattered every which way.
All right, so K is basically the volume knob on the loud music at our cocktail party. What about the second dial? The paper calls it beta, which they define as the inverse temperature. Now, temperature usually implies particles bouncing around really fast. Why is it inverse?
Well, in statistical mechanics, temperature is indeed about random kinetic energy. So inverse temperature is about the lack of it, or rather the strictness of the system. In this model, beta dictates how sharply the tokens want to align with each other.
I'm not sure I'm fully following that. How does a token want something?
Think of it as their sensitivity to the attention gravity. If beta is very high, the tokens are hypersensitive. Even a tiny, subtle similarity between two words will cause a massive gravitational pull between them. They are aggressively seeking alignment. But if beta is very low, they are sluggish. They will only pull together if they are virtually identical in meaning.
Okay, I have it. K controls how much random scattering is hitting the tokens, and beta controls how aggressively the tokens are trying to overcome that scattering to stick together. And based on these two dials, the paper proves a Shark global minimizer dichotomy.
Yes, and this dichotomy is the core of their entire discovery. They prove mathematically that when the system undergoes its phase transition, when the tokens finally overpower the noise and start clumping together, it can only happen in one of two completely different ways. It is either a continuous transition or a discontinuous transition.
I really want to spend some time on this because this dichotomy feels like the key to everything.
Yeah.
Let's look at the continuous transition first. How does that play out on our sphere?
A continuous transition is a smooth, gradual evolution. Think of water slowly freezing into ice in a normal freezer. As the temperature drops, or in our model, as the noise K decreases, the water molecules gently and predictably slow down. They start to gently link up and arrange themselves into a crystal lattice.
So if you were watching the tokens on the sphere, what would you actually see?
You would see them slowly drifting. The uniform spread would gracefully begin to gather into distinct, stable clusters. There's no sudden shock to the system. It's just a gradual reorganization of the geometry. The AI is smoothly sorting its concepts out.
That sounds ideal. It sounds stable. But then the paper contrasts this with the discontinuous transition. And I imagine this is where things get messy. What is the physical analogy for discontinuous?
The analogy here is supercooled water. Have you ever seen those videos where someone takes a very pure bottle of water out of the freezer and it's still entirely liquid?
Yes, and then they flick the bottle with their finger or slam it on the counter, and the whole thing instantly turns to solid ice in like 2 seconds.
Precisely. That water was cooled below its freezing point, but because there were no impurities for the ice crystals to form around, it remains stuck in a liquid state. But that state is incredibly highly unstable. The underlying tension is immense. All it takes is one tiny kinetic shock, a flick of a finger, and the entire system snaps into a solid state violently.
So translate that to our noisy transformer. What does a snap look like for these AI tokens?
In a discontinuous transition, the tokens are spread out evenly across the sphere. To an observer, the system looks stable, but it is a trap. The inverse temperature beta is too high. The underlying attention gravity is incredibly strong, but the tokens are deadlocked, trapped in this uniform grid by the noise.
Okay.
Then a tiny random fluctuation occurs, just a speck of Brownian noise pushing two tokens slightly closer together than they should be.
The flick of the finger on the bottle.
Exactly, and snap. The uniform spread catastrophically collapses. The deadlock is broken, and the tokens instantly and violently rush into massive, dense clusters. There is no smooth sorting. It is a sudden, extreme geometric shift.
I'm tracking the physics here, but I have to ask, so what?
What do you mean?
I mean, if I'm a user typing a question into ChatGPT, why do I care if the math inside the black box froze like normal water or snapped like supercooled water? We're talking about an AI processing language. What does a violent discontinuous snap actually mean for the text that spits out on my screen?
Right, this is where we have to extrapolate a bit, but it leads to a truly fascinating theory. This mathematical dichotomy could be the key to understanding why large language models hallucinate.
Hallucinations. You mean when I ask the AI a straightforward question and it suddenly confidently tells me a totally fabricated historical fact, or it just fixates on one weird word in my prompt and goes off on an unhinged tangent?
Yes, exactly. When a model hallucinates, it has essentially lost the broader context of your prompt. It's lost its balance. Now, map that onto our spherical geometry. If the tokens in your prompt are experiencing a continuous transition, the AI is gently sorting the concepts.
It's stable.
Right. It's building a cluster for the subject, a cluster for the verb, maybe a cluster for the tone. It maintains a balanced, nuanced representation of your entire sentence.
It's keeping all the plates spinning.
Exactly. But what if the internal parameters of that specific layer hit a discontinuous phase transition?
The snap. The supercooled water freezing instantly.
Right. If that happens, the attention mechanism violently overpowers the noise in an instant. All the tokens on the sphere might suddenly collapse into a single, overwhelming cluster of meaning.
Oh, wow.
The diverse, spread out representation of your sentence is instantaneously destroyed. The model gets sucked into a gravitational black hole of its own attention. It hyperfixates on one obscure aspect of the prompt, collapses all context into that single point, and spits out a hallucination.
That is incredible. So this incredibly dense math about McKee and Vlasov free energy and phase transitions isn't just an academic exercise. It's essentially providing a structural thermodynamic explanation for why an AI might suddenly lose its mind.
Exactly.
It's not just a glitch in the code. It is a violent phase change in the physical dynamics of its attention mechanism.
That is the implication. If we understand this mathematically, we aren't just shrugging our shoulders when a model fails. We are looking at the telemetry and seeing that the system literally shattered.
But if you are building one of these models, you obviously want to avoid the snap. You want your AI to have smooth, continuous transitions every time. You don't want the supercooled water. So how do you ensure that? Is it just trial and error? Do you just run the model a million times and tweak the dials until it stops hallucinating?
That's how a lot of AI engineering has felt in the past, honestly, trial and error. But this paper changes that entirely. The biggest breakthrough Munn and Rosenzweig achieved here is that they didn't just describe the dichotomy, they mathematically proved the exact hard border between the two states.
The magic threshold.
Yes, they denote it as beta star of D.
I want to break this down entirely. What is this threshold, and what does the D stand for?
The D stands for dimension. The authors proved that in every dimension greater than or equal to 2, meaning any spherical space, from a flat 2D circle all the way up to a 10,000 dimensional hypersphere, there is a unique exact threshold for the inverse temperature beta.
So they drew a permanent line in the sand.
Exactly. If your system's beta is less than or equal to this threshold, the transition is mathematically guaranteed to be continuous. The water will freeze smoothly. But the moment your beta crosses that line, if it's strictly greater than beta star of D, the transition is guaranteed to be discontinuous. The water will snap into ice.
How do you even go about calculating a universal line in the sand for something so complex? The paper says the mathematical condition to find this threshold involves setting a ratio of modified Bessel functions of the first kind equal to 1 divided by the dimension, d.
It's a lot, I know.
I'm not going to lie, modified Bessel function of the first kind sounds like a component of a warp drive from Star Trek. I am completely lost on what that actually is.
It is a heavy term, but the concept underneath it is something you've definitely experienced in the real world. Let's start with regular Bessel functions. Historically, these were mathematical tools developed to describe waves and vibrations, specifically in cylindrical or spherical shapes.
Okay, waves. Give me a physical example.
The most classic example is a circular drumhead. Imagine a timpani drum. When you strike it with a mallet in the center, the surface doesn't just bounce up and down uniformly. The impact creates a wave that ripples outward, hits the rigid edge of the drum, and bounces back toward the center.
Right, and the incoming waves and outgoing waves interfere with each other.
Yes, they create highly complex standing wave patterns. If you've ever seen sand sprinkled on a vibrating metal plate and it forms those intricate symmetrical geometric shapes, those shapes are physical manifestations of Bessel functions. The equations draw those rippling patterns.
That is a beautiful image. But how does the math of a vibrating drumhead apply to language tokens floating on a sphere inside an AI? The tokens aren't being hit with the drumstick.
Think about the attention mechanism again. The tokens are trapped on the curved surface of our unit sphere. When one token exerts its gravity on another, that influence is essentially radiating out across the curved surface. You can visualize the pull of attention as a wave of influence propagating through the space.
Okay, so a wave of meaning rippling across the sphere.
Exactly. The modified Bessel functions in this paper are essentially measuring how strongly these particles are communicating and interacting across the specific geometric curvature of the sphere. The modification just means these waves aren't oscillating up and down indefinitely like a drum. They describe a wave of influence that exponentially grows or decays based on distance.
So to find the exact tipping point between a smooth transition and a violent collapse, the authors are looking at a ratio between two different Bessel functions. They're essentially comparing two different modes of how these ripples of influence travel across the sphere.
Right.
And they proved that the exact moment that ratio hits 1 divided by the number of dimensions, you cross the border into a discontinuous snap.
That is a fantastic summary. It's an incredibly clean, elegant mathematical condition governing what is really a violently chaotic system.
But I want to push back on something here, or at least I want to explore a weird quirk in their data. The authors provide a table of numerical solutions. They actually ran the math and calculated the exact number for this threshold, beta star of D, across different dimensions.
Mhm.
And the numbers do something that feels completely counterintuitive to me.
Oh, what did you notice?
Well, in a two-dimensional space, which is basically just a circle, the threshold is roughly 2.44. Okay, fine. But when they calculate it for a 10-dimensional sphere, the threshold drops to 1.21. They go to 100 dimensions, it drops even further. As the sphere gets more dimensions, the threshold gets smaller and smaller. Why is that? Why does adding more space and more dimensions lower the threshold for a violent collapse?
That's a great observation. What you are noticing is a manifestation of something mathematicians call the curse of dimensionality.
The curse of dimensionality.
Yes, it is one of the most mind-bending concepts in geometry. Our human brains are hardwired to understand three-dimensional space. We evolved to navigate it, but mathematically, a sphere can have any number of dimensions, and something deeply weird happens to the volume of a sphere as the dimensions scale up.
Weird how?
Imagine peeling an orange. In 3D space, the peel is just a thin layer on the outside, and most of the orange is the juicy fruit inside. But if you have a 10-dimensional orange, the geometry distorts. Almost all of the volume of the orange moves to the peel.
Wait, what?
I know, it's weird. In high dimensions, vastly more of the sphere's surface area is concentrated near its equator. The space becomes incredibly vast, and almost all of it is essentially empty space. The points are pushed out to the extremities.
So a 10-dimensional sphere feels infinitely emptier than a three-dimensional sphere. The tokens are much further apart.
Exactly. They are isolated in this vast, incomprehensible expanse of empty geometric space. Now, remember what our inverse temperature beta does. It dictates how sharply the tokens want to align, how aggressively they pull together to overcome the noise.
Right. The strictness of the system.
In a low-dimensional space, like a 2D circle, things are relatively cramped. The tokens are already bumping into each other. To cause a sudden, violent collapse of the entire system, you need a high beta. You need a really strong, aggressive, attractive force to overcome the noise, because the noise is constantly disrupting them in that cramped space. That is why the threshold is high at 2.44.
Because there isn't enough room to build up unobstructed momentum.
Exactly. But in high dimensions, the tokens are floating in a void. Because there's so much empty room and the tokens are so isolated from each other, it actually takes less attractive force to cause a catastrophe.
I think I see it. Because they're floating in the void, if they feel even a moderate pull across that empty space, they start falling toward each other. And because the space is so vast, there's nothing in their way to disrupt them or stop them.
You've got it. The sheer geometric isolation means that the uniform, spread out state is incredibly fragile. Therefore, a much smaller alignment force, a beta of 1.21 or less, is enough to shatter the uniform state. Once they start falling, the momentum builds and it triggers a sudden discontinuous collapse.
That is brilliant, but it's also terrifying for an engineer. Because you might test your AI model in a simple 2D simulation, see that it is perfectly stable, and just assume you are safe.
And you would be completely wrong, because modern AI models like GPT-4 don't operate in 2 dimensions or even 10 dimensions. They operate in embedding spaces that have hundreds or thousands of dimensions.
Right, so this mathematical proof is showing us that as you scale an AI model up, as you give it more dimensions to work with, it becomes inherently mathematically more susceptible to these violent snaps.
Precisely.
The uniform stable state becomes a razor's edge. You cannot just assume the physics will scale smoothly. The fundamental geometry of the phase transition changes.
It is a stark warning embedded in the math.
Finding this exact threshold in arbitrary dimensions is a massive achievement. To prove it perfectly for any dimensions is a wild flex by the authors.
Oh.
But I really want to understand how they actually proved it, because they had to use a very specific toolkit to nail this down.
Yes, the heavy mathematical machinery. To prove this dichotomy is a universal law, they couldn't just run a simulation. They had to construct 2 separate proofs. First, they had to prove the continuous side that below the threshold, the system is unconditionally stable against any possible disruption.
Okay.
Second, they had to prove the discontinuous side that above the threshold, a specific disruption will instantly shatter the system.
Let's take the continuous side first. My notes here say they use the sharp Beckner-Onofre / logarithmic Hardy-Littlewood-Sobolev inequality alongside some Funke coefficient computations.
Oh boy.
I'm going to need you to save me here because I don't even know how to begin parsing that sentence. How does an inequality prove stability?
Let's step back from the names and look at the conceptual goal. Proving stability is one of the hardest things to do in mathematics. To prove that the uniform state where all the tokens are perfectly evenly spread out across the sphere is stable, you can't just test one or two scenarios. You have to prove that if you take that even spread and perturb it,
Perturb it meaning poke it, disrupt it.
right, if you stretch it, ripple it, bunch it up in a corner, or disrupt it in literally any conceivable way, the system will always naturally smooth itself back out to an even spread.
It's like dropping a boulder into a perfectly still pond and proving mathematically that the water will always, eventually, return to a perfectly still, glassy surface, regardless of how big the boulder is.
Yes, beautiful analogy. And on a sphere, the different ways you can perturb the surface are described by spherical harmonics. These are just complex wave patterns that wrap around a globe. The Beckner-Onofre inequality and its dual, the logarithmic HLS inequality, are incredibly powerful geometric tools that deal with these harmonics. You can think of them as placing a strict mathematical speed limit on entropy.
A speed limit on chaos.
Essentially, yes. The inequalities provide an absolute fundamental limit on how much the entropy, the spreading, chaotic force of the noise can change when you apply these harmonic waves. The authors use this inequality to weigh the spreading force against the clumping force across every possible wave pattern on the sphere simultaneously.
And what happens when they weigh them?
Well, by meticulously computing the Funk-Heck coefficients, which tie back to those Bessel functions measuring the wave ripples we talked about earlier, they prove that as long as your inverse temperature beta is below the threshold, the spreading force of the noise is mathematically guaranteed to be slightly stronger than the clumping force of the attention, no matter how the tokens are arranged.
So even if a random fluctuation accidentally clumps a bunch of tokens together, the math guarantees that the noise acts as an invincible shock absorber. It will always have enough power to vibrate that clump apart and smooth the sphere back out.
It is a foolproof, universal guarantee of stability.
Okay, I follow that. The continuous side is secured by the shock absorber of noise. But this is where it gets really interesting for me, because they had to prove the exact opposite for the discontinuous side. They had to prove that the millisecond you cross that threshold, the shock absorber catastrophically fails.
And this is perhaps the most elegant part of the entire paper. To prove the failure, they had to identify the specific flaw in the system. They call it a degree 2 quartic obstruction.
Degree 2 quartic obstruction. Okay, I'm going to need you to unpack this, because obstruction sounds like a physical roadblock, like a boulder sitting on a sphere. What is an obstruction in this context?
It's not a physical block. It is an obstruction to stability. It is a mathematical anomaly that prevents the system from remaining spread out. To understand it, we need an analogy involving acoustic resonance. Have you ever seen the demonstration where an opera singer shatters a crystal wine glass with their voice?
Yeah, they hit a really high, pure note, hold it, and the glass just explodes.
Exactly. Now let's translate that physics to our tokens. The wine glass is our uniform, perfectly spread out distribution of tokens. It seems solid. When the system is exactly at the critical threshold, the authors show that a simple basic disruption, a degree 1 spherical harmonic, is completely harmless.
What does a degree 1 disruption look like?
It is a gentle wave that essentially pushes tokens from the northern hemisphere to the southern hemisphere. It has two poles, it just wobbles the system.
So the singer hits a degree 1 note, the glass vibrates, the tokens wobble, but the structure holds. The glass doesn't break. You might look at that and think, great, the system is perfectly stable.
But the singer's voice isn't just one pure, simple note. It has overtones, hidden harmonics. What the authors discovered is that if you construct a complex disruption that mixes that harmless degree 1 wobble with a degree 2 component, everything changes.
What is a degree 2 component?
A degree 2 spherical harmonic is a more complex ripple. Instead of just two poles pushing north to south, it has four poles. It is a more intricate pattern of squeezing and stretching on the sphere. The authors discovered that when your inverse temperature beta exceeds the threshold, this specific hidden degree 2 ripple acts exactly like the resonant frequency of the wine glass.
Oh, wow. So the degree 1 wave was harmless, but this degree 2 harmonic bypasses the system's defenses.
Yes. The authors calculate the free energy of this mixed ripple up to the fourth power. That is why it is called a quartic obstruction. And they find that at order 4, the math suddenly violently flips.
Close how?
Below the threshold, the evenly spread out state always had the lowest free energy. It was the bottom of the hill. But the moment you cross the threshold and introduce this degree 2 ripple, the free energy of that complex rippled state suddenly becomes lower than the free energy of the perfectly even spread.
As we established earlier, the fundamental law of physics is that a system will always seek the lowest possible energy state.
Exactly. In plain English, the moment you cross the threshold, the math dictates that a tiny, complex, four-poled ripple in the tokens is suddenly preferable to being evenly spread out.
Wow.
The even spread becomes an illusion of stability. The moment that specific degree 2 ripple occurs, and in a noisy environment, random fluctuations guarantee it will happen instantly, the system realizes it can drop its energy by collapsing.
The singer hits the overtone, the energy cascades, and the glass shatters.
The uniform spread shatters and the tokens instantly snap into dense clusters. The quartic obstruction proves that smooth stability is mathematically impossible above the threshold.
That is just brilliant. It's like Munn and Rosenzweig acted as structural engineers. They examined the architecture of the AI's attention mechanism, and they found the exact harmonic frequency that shatters its context.
It's a great way to put it.
We have traversed some intense mathematical terrain here. Bessel functions, dimensional curses, quartic obstructions. But I want to zoom out for a second, because there's a moment in this paper that bridges this highly specific AI research to a much broader history of physics.
You're talking about the small beta limit.
Yes, buried in the text, the authors make a remark about what happens if you take their equations for tokens on a 2D circle and you dial the inverse temperature beta all the way down until it is very, very small.
Right, and when you do that, the complex equations simplify, the higher order interactions fade away, and the formula converges exactly onto the mathematical drift of something called the identical oscillator Kuramoto model.
And when I read that, it blew my mind. Because I know the Kuramoto model, it's famous. It was developed in 1975, right?
By Yoshiki Kuramoto, yes. It is one of the most famous mathematical models in the world for describing biological synchronization.
Let me set the scene for the listener, because this is the real aha moment of the deep dive. The Kuramoto model answers a question that has baffled scientists for centuries. How do independent, chaotic, mindless things suddenly learn to act in perfect unison without a leader?
Yeah.
The classic example is fireflies. If you go to certain mangrove forests in Southeast Asia, you will see thousands of fireflies flashing their lights randomly in the dark. It is complete chaos.
A high entropy state.
Right. But as the night goes on, the fireflies start observing each other. They possess these internal phase oscillators. They adjust their internal rhythm based on the flashes of their immediate neighbors. And eventually, through this localized pulling and pushing, the entire forest of thousands of bugs is flashing on and off in perfect, synchronized, blinding unison.
It is spontaneous order emerging from chaos, and it applies to more than just bugs. If you hang a dozen pendulum clocks on the same wooden wall and start them swinging at random times, the tiny vibrations traveling through the wood will eventually cause all the pendulums to lock into the exact same rhythm.
It's the universal math of synchronization. And what Munn and Rosenzweig have casually pointed out in this paper is profound. The exact same mathematical equations that dictate how biological fireflies sync their flashes in a dark forest are the exact same equations describing how fragments of human language synchronize inside a neural network's attention mechanism.
Exactly. The tokens are the fireflies. They are flashing their vectors at each other, pulling on each other, trying to sync up and form a coherent thought out of the chaos of the Brownian noise. Language processing in AI isn't just a metaphor for synchronization. Mathematically, at the small beta limit, it is identical to it.
But there is a reason this paper is a breakthrough, and not just a repetition of 1970s math. It comes back to the dimensions, right?
Exactly. The original Kuramoto model and almost all the subsequent work on it was focused on systems operating on a circle, a one-dimensional line wrapped into a 2D space. That is fine for a firefly's flashing rhythm, which is a simple cycle, but real AI doesn't live on a 2D circle.
No, it lives in the 10,000-dimensional hypersphere, where the cursive dimensionality is waiting to shatter the glass.
Yes. By proving that this phase transition holds true in arbitrary dimensions, and by finding the exact equation for that threshold, the authors haven't just noted a cute historical parallel to fireflies. They have scaled the math of the fireflies up to the incomprehensible scale of a digital superbrain. They have provided the foundational blueprint for high-dimensional synchronization.
So let's wrap this all together. What is the ultimate so what of this paper? If I am an engineer at a major tech company and I'm building the next generation model that is going to replace GPT-4, why is this math critical to my job?
It is critical because you are trying to build an incredibly powerful engine, and this paper just handed you the thermodynamic limits of that engine. If you know the exact mathematical boundary where token attention violently collapses into a hallucination, you can design your architecture to explicitly avoid it.
You don't have to guess anymore.
But it goes deeper than just avoiding failure. You might actually want to design your model to sit right on the edge of that threshold.
Wait, why? Why would you want to flirt with the discontinuous snap?
Because in complex systems, the most powerful expressive computation actually happens right at the boundary of a phase transition. It is known as the edge of chaos.
Okay.
If an AI model is too stable, deeply embedded in the continuous zone, it might be too rigid. It might be too slow to learn complex relationships, too bound by the noise to pick up on the subtle nuances of your prompt.
It would be safe, but stupid.
But if it crosses the threshold, it collapses into a hyperfixated hallucination. The sweet spot, the peak intelligence, is balancing perfectly on the razor's edge between the two. If engineers can use this paper's blueprint to mathematically tune the noise and the temperature of their layers, they could theoretically maximize the model's learning efficiency and its expressive power without ever falling over the cliff.
It's like finding the exact aerodynamic limit of a fighter jet. You want to fly it as fast and maneuverable as physically possible without ripping the wings off. This paper gives them the exact formula for the structural integrity of the AI's wings.
It completely shifts AI development from being a dark art of trial and error alchemy into rigorous, predictable mathematical engineering.
Wow, what an absolute journey. To recap this deep dive for everyone listening, we took a highly intimidating math paper, and we discovered that inside the black box of a transformer model, words are acting like physical particles trapped on a hypersphere. They are locked in a thermodynamic tug-of-war between the gravity of the attention mechanism, which wants to cluster meaning, and the repelling force of isotropic noise. And by utilizing the math of vibrating drumheads and quartic obstructions, the authors prove there is a specific threshold beta star of D that dictates whether the system will sort itself smoothly or snap violently and hallucinate.
What stands out to me at the end of all this is the sheer universality of the mathematics. We are looking at equations, Bessel functions, Makinin-Vlasov equations that were designed centuries ago to study fluid dynamics, heat transfer, and physical waves. They were built to understand the physical universe.
Yeah.
Yet they are exactly the tools required to map the digital brain of artificial intelligence. It strongly suggests that the laws of computation and the laws of physics are far more intertwined than we ever realized.
Which leaves us with a final thought to mull over. A question directly for you, the listener, as you go about your day.
Yeah.
We build these large language models to mimic human thought. We talk about them as if they understand context or learn to speak. But if the attention mechanism in our most advanced AI is mathematically identical to physical particles seeking the lowest state of free energy, if a thought forming in a neural network is governed by the exact same equations as a cloud of fireflies mechanically syncing their lights, does that mean the way AI understands language is just an illusion? Is artificial intelligence at its absolute core not a process of logic or reasoning at all, but simply a highly complex, high-dimensional simulation of thermodynamics?
That is the philosophical cliff this paper leaves us standing on.
It certainly changes how you look at the blinking cursor the next time you type a prompt, doesn't it? Yeah. Thank you for taking the plunge into the heavy math with us today. It was dense, but seeing the physical laws hidden inside the code is completely worth it. Stay curious, and we will see you on the next deep dive. Right now, inside the neural network of whatever artificial intelligence you most recently used, there is this violent, microscopic tug-of-war happening.
Yeah, violent is honestly the perfect word for it.
It really is. On one side of this invisible rope, you have this intense gravitational attraction. It's a force that's, desperately trying to pull every single piece of information into just one dense cluster of meaning.
Right, the system wants to pull things together.
Exactly. But then on the other side of the rope, you have pure chaotic noise.
Yeah.
Just violently jiggling all those data points apart, forcing them to stay scattered and distinct.
It's a constant, massive struggle.
And the wild thing is, the AI's ability to actually answer your prompt, to give you a coherent thought instead of just like a blur of static, that depends entirely on who is winning that microscopic tug-of-war.
It's such a remarkable way to visualize it, and it completely runs counter to how we usually think about software,
Yeah, we're trained to think of computers as these rigid, step-by-step logic engines.
Exactly. You put a prompt in, the code executes a decision tree, and an answer spits out. But modern large language models, the massive transformer architectures we all use today, they just do not behave like calculators.
Oh, no, they might not.
At a certain scale, they literally start behaving like organic physical systems.
And today, you and I are going to look under the hood of those organic systems. Welcome to the deep dive. We are completely abandoning the traditional language of computer science for this one.
No Python scripts today.
Nope, no talk of Python or API calls. Instead, we are looking at AI through the highly rigorous, just beautifully complex lens of advanced mathematics and physical geometry.
And we're pulling this from a really fascinating paper, right?
We are. It's a paper titled Phase Transitions for the Noisy Transformer Model in Arbitrary Dimension, and it's written by Kyunghoo and Matthew Rosenzweig.
It is just a phenomenal piece of work. Munn and Rosenzweig, they've taken the core mechanism of modern AI, the transformer, and modeled it as a high-dimensional physical environment.
Which is mind-blowing.
It is. They aren't just looking at the text outputs. They are looking at the fundamental geometry of how an AI actually focuses its attention.
So our mission today is to translate this cutting-edge math into human terms for you. We want to really understand the hidden physical forces that dictate how a scattered cloud of data suddenly just bam snaps into a brilliant, coherent answer.
And maybe more importantly, how the system avoids total collapse along the way.
Right. The collapse is the big danger. So let's start with the stage where all of this happens. The authors focus on a mathematical model they call unnormalized self-attention, or the USA model.
But before we even get to the attention part, we really need to talk about where the data actually lives.
Yeah, let's break that down. In a modern transformer, the system processes information using tokens, right?
Correct. And for the listener, you can think of a token as a piece of data. It could be a word, a part of a word, or even just a specific concept.
Okay, so I've got my token. It's a word. But to understand the physics here, we have to look at this very specific step in the architecture called layer normalization.
Yes, because in a neural network, a token isn't actually a word, it's a vector.
A vector, so like an arrow pointing in a certain direction.
Essentially, yes. It's a string of numbers pointing in a specific direction in a mathematical space. But
Yeah.
without constraints, as the network processes these vectors, they can just grow infinitely large.
Which would completely break the math, I'd assume.
It shatters the math. So layer normalization solves this by essentially dividing every vector by its own magnitude.
So it forces every single token to have an exact mathematical length of 1.
Precisely. And this creates a really profound geometric reality. If you have a center point, an origin, and you say that every single token must be exactly a distance of 1 away from that origin, what shape have you just created?
Well, if every point is perfectly equidistant from the center, that's a sphere.
Exactly, a sphere. In the paper, they refer to this as the unit sphere, and the notation is zealot 1.
Okay, wait, let's unpack that notation. The dollar stands for the dimension of the space, right? But why the -1?
Good catch. Think of a 3D physical space, like the room you're in. The space is three-dimensional, but the surface of a sphere inside that room is only two-dimensional. You only need latitude and longitude to find a point on it.
Oh, right. So the surface is always one dimension lower than the space it lives in.
Exactly. So the moment you apply that layer normalization, these tokens aren't just floating around in some infinite abstract void.
They are mathematically locked onto the surface of a high-dimensional sphere.
Yes, that is our stage.
Okay, we have our stage. We have this spherical universe populated by all these token vectors. Now, how do they actually interact with each other?
Well, the paper talks about the self-attention mechanism, and they describe it using query key inner products.
Okay, query key inner products. That sounds like heavy jargon. Let's translate that.
If the sphere is the universe, self-attention is the gravity.
I like that.
When the AI processes a sentence, it updates its understanding of one token by comparing it mathematically to all the other tokens. It's constantly calculating the similarity between them.
So from a physics standpoint, this similarity acts as an attractive force.
Exactly. The self-attention mechanism is actively pulling these points together across the surface of the sphere, clustering similar concepts closer and closer.
I'm trying to picture this physically. Let's say we have a massive cocktail party,
Okay, a cocktail party.
and the guests are the tokens. At the beginning of the night, everyone is spread out pretty evenly across the room. That's our sphere.
Right.
But as conversations start, guests naturally gravitate toward the most interesting discussions in the room. So the attention they share is literally the gravity pulling them together into tight little groups.
That analogy works perfectly. The shared attention is an attractive potential.
Okay, so if you and I are both tokens representing concepts related to, say, astrophysics.
Then the attention mechanism calculates a high similarity between our two vectors, and it physically pulls our positions closer together on the sphere.
So the more relevant the concepts are, exactly like guests finding a common interest, the stronger the pull.
Yes. But if we follow that cocktail party analogy to its logical conclusion, there's a huge problem.
Right, because if gravity is the absolute only force at play, and it just relentlessly pulls similar things together, wouldn't the party just completely collapse?
It would.
Like one person tells a really good joke, everyone rushes over, and suddenly you just have this terrifying singularity of guests crushing each other in the exact center of the room.
It would be a disaster.
If the AI tokens just attract each other endlessly, wouldn't the whole network just collapse into a single dense point of data?
You've just identified exactly what the paper calls small-scale collapse.
No scale collapse.
Yes, if the attractive force of self-attention operates in a total vacuum, without any resistance at all the tokens inevitably merge into a single, undifferentiated point on that sphere.
Wow. So the AI would lose all nuance.
Completely. It wouldn't be able to distinguish between a noun, a verb, or even the context of a sentence. It would just output a single, meaningless drone.
So gravity cannot be the only thing happening on this sphere. There has to be some sort of counterforce pushing back against the attention to keep the tokens from collapsing into a black hole.
Which brings us to the crucial second component of the USA model, the noise.
The noise, okay.
To prevent that small-scale collapse, the system structurally requires a constant injection of chaos. In the mathematical framework of the paper, this is introduced as isotropic Brownian noise.
Okay, I need to stop you there because isotropic Brownian noise sounds incredibly dense. Let's really break that down for the listener. So, Brownian motion.
Okay.
That's the random, erratic jiggling of microscopic particles, right?
Yeah.
Like you look at a piece of dust dancing in a sunbeam.
Or pollen floating in a tiny drop of water under a microscope. It's constantly being bumped by invisible molecules.
Right, so that's the exact physical mechanism we're talking about here. It's just constant random perturbation.
Exactly. And the word isotropic simply means that this random jiggling happens uniformly in all directions across the surface of our high-dimensional sphere. No single direction is favored.
So while gravity is aggressively trying to pull the tokens together into a clump, this isotropic Brownian noise is constantly shaking the sphere.
Yes, it's forcing the tokens to randomly jitter and drift apart.
But the paper introduces another term here that I really want to unpack. Because when you have a massive number of tokens, which, a real AI certainly does, the authors state that this system becomes a McKean-Vlasov diffusion.
Right, in the mean field limit.
Yeah, and the mean field limit. What does that actually mean in plain English?
So the mean field limit is a brilliant trick physicists use when a system just gets way too crowded.
Okay.
If you have, say, 5 tokens on a sphere, you can calculate the exact gravity and the exact noise affecting each individual token. But if you have billions of tokens, the math becomes completely impossible to compute.
The computer would just freeze.
Exactly. So instead of tracking individual particles, you zoom out. You track the overall density of the particles as a single fluid.
Oh, okay. So a McKean-Vlasov diffusion is simply the mathematical equation that describes how that fluid of tokens flows and spreads out over the sphere.
Exactly, when it's being pulled by gravity, but also randomly jiggled by noise.
So going back to our party, instead of watching individual guests bumping into each other, we were basically looking down from the ceiling with a heat camera.
That's this great visual.
We're just watching the overall flow of body heat across the room as the crowd shifts around.
Yes. And understanding that flow is critical because it reveals a massive philosophical shift in how we view machine learning.
How so?
Well, usually in software engineering, noise is the ultimate enemy. It's an error. You want a clean, pure signal. But the authors explicitly state that at the variational level, this noise regularizes the attractive attention dynamics.
So it's a structural requirement. Noise isn't a bug in the code at all.
Yeah.
It's literally a feature keeping the system alive.
Fundamentally, the entire AI is governed by this thermodynamic tug-of-war. The system is always striving to minimize what physicists call free energy.
Free energy.
Yes, and free energy is a very delicate balance. It is calculated by taking the interaction energy, which is the order, the tendency of tokens to pull together, and subtracting the entropy.
And entropy is the chaos, the tendency of the noise to spread the tokens out evenly.
Exactly.
It's like injecting forced randomness into a corporate brainstorming session.
Oh, how do you mean?
Like, if everyone just agrees with the first loud voice in the room, you get this massive, uncreative clump of groupthink.
The small-scale collapse.
Exactly. But the forced randomness, the noise, forces the ideas to stay slightly scattered and diverse until a genuinely strong concept creates enough gravity to legitimately pull everyone together.
The paper actually quantifies this specific tug-of-war using a variable called the coupling strength, which they denote with the letter $2.
Okay, so $2 is the coupling strength.
You can think of the coupling strength dollars as the dial that directly controls the gravity. But, and this is highly important, $2 is the mathematical inverse of the noise strength.
Okay, so they operate on a seesaw. If I crank up the coupling strength dollar, I am simultaneously turning down the noise.
Correct. A high coupling strength means the noise is very low, the attractive force of attention absolutely dominates, and the tokens desperately want to clump together tightly.
And conversely, a low dollar means the noise is very high, the chaotic jiggling completely overpowers the gravity, and the tokens fly apart.
Spreading uniformly across the entire surface of the sphere.
So if you were designing this AI, you were constantly turning this dollar dial, trying to find the exact sweet spot between total chaos and total collapse.
You are.
But here's what I am wondering about that dial. If you slowly turn it, if you slowly increase the coupling strength, ramping up the gravity and fighting against the noise, the system can't just smoothly exist in a state of perfectly balanced tension forever, can it?
It cannot.
Eventually, one side has to definitively win.
And that inevitable breaking point is the absolute central focus of the paper. In physics, that breaking point is called a phase transition.
A phase transition.
Munn and Rosenzweig set out to mathematically prove exactly when and how this AI universe transitions between its two fundamental states.
Okay, let's define those two states really clearly for the listener. On one extreme, we have what the paper calls the uniform density state.
Right.
This is when the noise is winning the tug of war. The tokens are evenly spread across the entire surface of the sphere.
From an information perspective, the uniform density state represents total confusion or maximum entropy.
So every token is just randomly jiggling, equally far from every other token.
Yes, the AI has not focused attention on anything specific. It's just staring at a wall of static.
And on the other extreme, we have the clustered states.
This is where the noise has been overpowered by the coupling strength.
The tokens have gathered to form distinct, tight concepts. The AI has successfully parsed the prompt, grouped the relevant ideas, and is ready to actually generate a coherent word.
The burning question the authors ask here is, at what exact mathematical threshold, a point they denote as TBCR, does the uniform measure cease to be the global minimizer of the free energy?
In other words, at what exact microsecond does that scattered cloud of data finally decide to snap together into a focused cluster?
Exactly.
I kind of visualize this like water turning into ice.
Oh, that's a brilliant analogy. Walk me through it.
Well, having high noise in the AI is like having high heat in a pot of water.
Mm-hmm.
The thermal energy keeps the water molecules bouncing around randomly in a liquid state.
Mm-hmm.
That's our uniform density.
Right, maximum chaos.
But lowering the noise, which means increasing that coupling strength dollars, is like dropping the temperature of the water. You drop it, and the molecules get more and more sluggish.
Yeah.
Until suddenly, you hit exactly 32 degrees Fahrenheit and boom, ice crystals form. The molecules lock into a solid, structured cluster. The liquid has undergone a phase transition into a solid.
It is a phenomenal way to visualize it because it perfectly sets up the primary mathematical conflict the authors had to solve here.
Which is what?
Well, when you freeze water, you might intuitively assume the transition is just a smooth, gradual slowing down of molecules.
Sure, like a dimmer switch.
But phase transitions in nature can happen in two completely different ways. And Munn and Rosenzweig proved that this AI model also has two completely different ways of waking up or focusing its attention.
They established what they call a sharp global minimizer dichotomy.
A dichotomy, meaning the system truly has a choice in how it freezes.
Yes. They outline the exact mathematical conditions under which the transition is continuous, meaning the data clusters smoothly and gradually, versus when the transition is discontinuous.
Discontinuous meaning the data suddenly and violently snaps from total chaos into a tight cluster.
I want to make sure I grasp the profound difference between those two things. A continuous transition is that like the water molecules gently locking arms one by one until a slush forms and then eventually it's solid ice.
In thermodynamics, we call that a second-order phase transition. As you slowly cross the critical threshold, the uniform chaotic state slowly deforms. The change in the system state is entirely continuous.
Okay, slush, I get that. but a discontinuous transition.
A first-order phase transition. It is radically dissonant. It is perfectly abrupt.
Abrupt how?
The system jumps from a uniform cloud to a tightly focused cluster instantly, with absolutely no intermediate states. The uniform state is perfectly stable one moment and then violently collapses into a solid cluster the next.
So the AI can either slowly gather its thoughts into slush, or it can have this sudden violent epiphany where everything just snaps into focus at once.
Exactly.
But what dictates which path it takes? I mean, why would it freeze smoothly one time but snap violently the next?
To answer that, we have to look at the specific mathematical threshold discovered by the authors, and this is where the paper becomes truly breathtaking.
Why is that?
Because this threshold doesn't rely on the speed of the processor or the size of the training data, it relies entirely on the geometry of the sphere itself. It relies on the dimension.
Oh, wow. This is the main theorem of the paper.
It is.
The authors prove that for every dimension dollars that is greater than or equal to 2, there's a unique mathematical tipping point.
They call this threshold beta star as a function of the dimension dollar.
We should definitely clarify the variables here. So beta represents the inverse temperature of the system.
Right. And in the context of our mathematical model, it acts in tandem with our coupling strength. A high beta means low temperature, which means low noise and strong attention.
So beta is the magic number. It's the exact coordinate where the rules of the universe change.
Yes. And here is the profound dichotomy they proved. If your system's beta is less than or equal to this magic beta threshold, the transition is continuous.
Continuous, the slush.
Exactly. The authors prove that the uniform scattered density remains the unique global minimizer of the energy up to a specific linear stability threshold, which they call Kara.
Queris.
Yes. When the system crosses that Kara line, the change into clustered focus happens gradually. The water freezes smoothly into slush. The mathematics show that the system slowly loses its preference for chaos.
The entropy gently yields to the interaction energy.
Precisely.
Yeah.
But if your beta is strictly greater than beta, the entire dynamic flips.
It becomes discontinuous.
The transition becomes completely discontinuous. The uniform density loses its global minimality strictly before it loses linear stability.
Okay, this is perhaps the most counterintuitive part of the entire paper, and it is crucial we explain the mechanics of it. What does it actually mean for a physical system to lose global minimality before it loses linear stability?
It sounds like it's a total paradox, right?
It really does. If something is mathematically stable, how can it not be the minimum energy state? Doesn't nature always seek the absolute lowest energy state available?
It does, but nature can be tricked by local topography.
Tricked how?
Imagine a massive, steep volcano. Now imagine that right at the very peak of this volcano, there is a tiny, shallow crater.
Okay, I have the picture in my head.
And resting perfectly in the exact center of that shallow crater is a boulder.
So the boulder is at the very top of the mountain, but it's sitting in a little dip.
Right. Now, locally, which mathematicians call linear stability, that boulder is perfectly stable.
Because if you give it a tiny push, a small perturbation, it just rolls up the side of the little crater and settles right back into the center.
Exactly. From the boulder's perspective, it is in the lowest possible energy state. The system absolutely believes it is mathematically optimal.
Because it can't see over the lip of the crater.
Mm-hmm.
The uniform, chaotic state of the AI thinks it's the best possible configuration.
You've got it. But global minimality looks at the entire landscape, the entire volcano.
Right.
And while the boulder is locally stable in its little crater at the peak, the true global minimum is actually thousands of feet below, at the base of the volcano.
Oh, man.
When Munn and Rosenzweig state that the system loses global minimality before linear stability, they mean that as you change the coupling strength, a deep valley suddenly opens up at the bottom of the volcano.
So the system is just tricked into thinking the scattered, uniform state is perfectly stable in its little crater.
Exactly. But mathematically, a highly clustered state at the bottom of the mountain is now vastly more efficient.
Oh, wow. So the AI is sitting there in a scattered state of static, actively resisting the urge to focus because it feels locally stable. But the tension is building.
The true minimum energy state is calling to it from the bottom of the mountain, but it's trapped in the crater.
And then, because the system is constantly being jiggled by that isotropic Brownian noise we talked about, eventually a large enough random jolt hits the system.
Yes. The noise pushes the boulder just hard enough to clear the lip of the crater.
And it doesn't just slide down slowly. It violently plummets down the steep side of the volcano to the true global minimum.
Yes. The system undergoes an abrupt, discontinuous jump from total chaos to highly clustered attention. There is no intermediate slush. It snaps instantly.
That is a staggering way to visualize how a neural network processes information. The system literally traps itself in a false sense of stability and then violently course corrects.
It really is beautiful mathematics.
But I have to push back here, because we were talking about geometry and dimensions.
Okay, pushback.
The paper frames this around an arbitrary dimension dollars, but in a real large language model-like, the kind of AI running on massive server farms right now. The embedding dimension, the dollar we were talking about, isn't just 2 or 3 like the physical space we live in.
No, it's massive.
These models represent tokens in thousands of dimensions to capture the nuance of human language. Dollars can be $4,096 or even $8,192.
Very true.
So I
That's
just cannot
elsewhere.
imagine that this delicate mathematical balance between a tiny crater and a steep volcano holds up when the sphere exists in 8,000 dimensions.
Yeah.
Doesn't the math just completely break down at that scale?
It is a highly rigorous question, and it's exactly where the authors focused a major portion of their proof.
Oh, really?
They knew that for this math to apply to real AI, it had to scale to infinity. So they performed what is called a large dollar expansion.
A large doll expansion.
Yes, they analyzed the exact behavior of this beta threshold as the dimensions grow infinitely large.
Mhm.
And they discovered that it doesn't break down at all, it converges.
It converges. To what?
They proved that as unborrowed gets huge, the threshold bore approaches a very specific asymptotic formula. $1 plus 2D plus 1D22.
Okay, let me do the math on that in my head.
Yeah.
If the angle dollars is a massive number like 4,000, then 2 divided by dollars is essentially 0.
Right.
And 1 divided by $2 is even closer to absolute 0. So the entire formula just collapses down to the number 1.
Precisely. They proved that the threshold function is strictly decreasing. The higher the dimension of the AI's understanding, the lower this beta star threshold becomes.
Creeping closer and closer to exactly 1, but never going below it.
Yes. It gives computer scientists a precise mathematical map of exactly how high-dimensional AI models will behave under varying levels of noise, regardless of whether they have 10 dimensions or 10,000.
It's incredible that such a complex system of billions of interacting parameters basically boils down to such an elegant asymptotic limit.
It's the beauty of physical laws.
But there's another extreme limit they explore in the paper that caught my eye. They look at the small battle limit. What happens when the attractive force of gravity is incredibly weak, almost non-existent, compared to the overwhelming chaos of the noise?
This is where the paper connects modern artificial intelligence to classical biological physics.
Biological physics.
Yes. When you study the small beta limit, when the gravity is just a whisper against a roaring hurricane of noise, the complex equations governing these AI tokens on a high-dimensional sphere simplify dramatically.
Okay.
And when they simplify, they perfectly match a famous set of equations known as the Kuramoto model.
The Kuramoto model. I actually know this one. This is the mathematics used to describe spontaneous synchronization in nature, right?
It is.
The classic example is the fireflies. If you go into certain forests in Southeast Asia, you have thousands of fireflies flashing completely randomly. It's total visual noise.
Exactly.
But over time, they slowly influence each other until eventually they spontaneously synchronize, and the entire forest flashes perfectly in unison.
Yes. The Kuramoto model describes coupled oscillators entities that have their own rhythm but are weakly influenced by the rhythms around them.
Wow.
When you turn down the beta 9 in this AI model, it reveals a profound reality. The mechanism a cutting-edge transformer uses to gather textual data out of the noise to answer a human prompt
Yeah.
is mathematically identical to biological entities spontaneously syncing their rhythms in a forest.
That is just beautiful. The AI isn't a calculator. It's literally a forest of digital fireflies trying to sync up their flashes through the static.
It really shifts your perspective.
But I have to ask,
Mm-hmm.
proving all of this mathematically, proving this continuous versus discontinuous dichotomy, proving the large dimension expansion, proving the connection to fireflies across literally any dimension up to infinity, you can't just do that with standard high school
Oh,
calculus.
absolutely not.
To pull this off, Munn and Rosenzweig must have had to pull out some incredibly heavy esoteric mathematical machinery.
They did. Proving the behavior of interacting particles on a sphere in arbitrary dimensions requires geometry that is, quite frankly, exceptionally hostile to human intuition.
Hostile is a good word for it.
Which is why we need to look at the specific mathematical tool belt they use to build this proof.
Because you can't just visualize a 4,000 dimensional sphere in your head and eyeball the answer. You need airtight mathematical constraints. So what was the primary tool they used to control the chaos of this high-dimensional universe?
To prove that the uniform state is stable under certain conditions, they had to generalize previous two-dimensional work by utilizing an absolute powerhouse of an inequality.
Okay, lay it on me.
It's known as the Sharp-Beckner-Onofre inequality on the sphere,
Oh, wow.
which is mathematically equivalent to the logarithmic Hardy-Littlewood-Sobolev inequality, often just abbreviated as the HLS inequality.
Okay, the Sharp-Beckner-Onofre logarithmic Hardy-Littlewood-Sobolev inequality. That is quite a mouthful.
It's a lot.
But what does this inequality actually do functionally within the proof? Like, what is its job?
In the simplest terms, this inequality provides the authors with what is called a coercive entropy estimate.
A coercive entropy estimate. I want to make sure I understand the mechanism here. How does one coerce entropy?
Think of it as a strict mathematical speed limit on order.
A speed limit on order. Okay.
When you are trying to prove that the system will remain in that chaotic uniform state, when you are trying to prove the continuous transition, you have to mathematically guarantee that the entropy, the noise, is strong enough to crush any tiny ripples of order that try to form.
Because if a few tokens randomly bump into each other and try to start a cluster, the entropy must forcefully dissolve them.
Exactly. The Beckner-Onofre inequality allows the mathematicians to rigorously bound the interaction energy by the entropy. It mathematically guarantees that the chaos is coercive enough to prevent premature clustering.
So it proves that the noise acts as an impenetrable shield against gravity, up to a very specific threshold. But to actually apply this inequality, the paper mentions they had to break the uniform state down into its component frequencies. They use something called spherical harmonics.
Yes, spherical harmonics.
And this is a concept I really want to unpack because it feels central to how the transition actually physically happens.
It is entirely central. Spherical harmonics are the geometric foundation of how the sphere vibrates.
Yeah.
How do you visualize them?
I think about it like the surface of a drum.
A drum.
Yeah. When you strike a drum head, the skin doesn't just bounce up and down as one perfectly flat surface. The vibration breaks down into a complex combination of fundamental frequencies and overtones.
Right, the acoustic properties.
Exactly. You have the main deep boom, which moves the whole center of the skin, but then you have these complex ripples and ridges of sound moving across the edges.
That's a great physical corollary.
Spherical harmonics are the exact same concept, but instead of a flat 2D drum head, you are ringing a multidimensional sphere like a bell. The tokens trying to pull together and cluster are like the acoustic vibrations rippling across the surface of that sphere.
That is a highly accurate way to conceptualize it. The uniform, perfectly scattered state of the AI is like the drum sitting in total silence.
Okay.
When tokens start to cluster, they are actually exciting the higher overtones or higher degrees of these spherical harmonics. The degree 1 harmonic is the simplest vibration. It's like all the tokens rushing to one single pole of the sphere, like a drum head just bowing in the middle.
But the authors don't focus on that simple degree 1 overtone.
No, they don't.
The paper zeroes in on a very specific, much more complex vibration. They identify what they call the degree 2 quartic obstruction.
The quartic obstruction.
You know, I want to really understand the mechanism of this obstruction. We talked earlier about the boulder trapped in the crater, right? And how a discontinuous jump happens when a deeper valley suddenly opens up. Is this quartic obstruction the mathematical shovel that digs that deeper valley?
You synthesized those two concepts perfectly, yes.
Yeah.
The quartic obstruction is the shovel.
Okay, so how does it work mechanically?
Here is how. When the AI undergoes a smooth, continuous transition, the system slowly loses stability primarily in that simple degree 1 overtone. The sphere just gently bulges toward one side.
Right.
But the authors discovered that when the ratio of the eigenvalues for the degree 2 harmonic crosses a very specific boundary,
Wait, what boundary?
specifically when the ratio crosses the $5, when that happens, the geometry of the energy landscape violently changes.
So the degree 2 overtone basically hijacks the system.
It does.
But why is it called a quartic obstruction?
Because the mathematics describing this specific overtone rely on a quartic equation, a term raised to the power of 4, like 6 by 40 SOR.
Okay, power 4.
Think about the shape of a graph for a moment. If you graph a quadratic equation like 6 by 42, it forms a gentle parabola, a smooth bowl.
Right, a standard U shape.
That represents the smooth, continuous transition. The boulder rolls gently down the side of the bowl,
Makes perfect sense.
but a quartic equation, 6 by over 4 dolls, behaves very differently. Near zero, And 644 graph is incredibly flat, much flatter than a parabola. It looks perfectly stable.
Ah, I see.
But once you move just slightly away from zero, the graph drops off precipitously. It is incredibly steep.
Oh, so the Cordic equation is what creates that local flat crater at the top,
Yeah.
but also creates the massive, steep drop-off immediately outside of it.
Exactly. When that degree 2 overtone mixes with the system, the quartic term completely takes over. It abruptly and dramatically lowers the free energy of the system far below the uniform state, creating that steep plunge.
Wow.
The degree 2 quartic obstruction is the literal mathematical proof that the hidden valley exists, which proves the existence of the sudden, violent jump into a clustered state.
That is just brilliant. The power of 4 flattens the local crater and
Yeah.
steepens the cliff. To actually find the exact boundaries of this cliff, though, to know exactly when that Ing-dollar ratio is crossed, the paper mentions a final tool, the Funk-Heck-Bessel coefficient computation,
It's quite the name.
which just sounds like they are mapping the exact acoustic properties of our multidimensional drum with terrifying precision.
That's precisely what they're doing. Working in arbitrary dimensions means you can't rely on simple trigonometry. The Funk-Heck formula, combined with modified Bessel functions, allowed the authors to compute the exact, pristine eigenvalues of the attention kernel.
So give them the exact numbers they needed.
It gave them the exact numerical coordinates needed to prove exactly when that quartic overtone would become an obstruction. It is an elegant, airtight piece of mathematical physics applied to machine learning.
It really is a masterpiece of interdisciplinary math.
Absolutely.
And having traversed all of this, the geometry of layer normalization, the coercive entropy estimates, the delicate balance of Brownian noise and attention gravity, and the sheer cliff faces of quartic obstructions, I think it's time to pull back.
Yeah, let's zoom out.
We need to look at the forest rather than the equations and bring this back to your everyday reality as a listener.
Let's synthesize the core insights. What have Mann and Rosenzweig actually proven about the technology we use every day?
Well, the paper proves, with absolute mathematical certainty, that the way a modern large language model focuses its attention is not just a rigid series of logical if-then statements.
No, not at all.
It behaves identically to a physical system undergoing thermodynamic phase transitions on a high-dimensional sphere.
It is a universe of data particles governed by physical laws.
And the nature of that AI's thought process, whether it smoothly and gently gathers its ideas into a cohesive answer, or whether it violently snaps into focus from a state of total scattered chaos, depends entirely on two fundamental properties.
Which are the dimension of the data it's working with and the exact strength of the noise actively fighting against the attention.
Exactly. So as a listener, the next time you open a generative AI, the next time you type a prompt into your phone or your browser, remember what is actually happening under the glass.
It's not just a calculator.
No, you aren't just querying a calculator. You are essentially poking a high-dimensional physical system. You are watching billions of tokens on a sphere delicately balancing chaotic noise and gravitational attention, hovering right on the very edge of a discontinuous phase transition.
All just to summarize an email or write a recipe?
Right, it makes the active computation feel incredibly organic and almost biological. Which leaves me with one final unmentioned idea to ponder, a provocative thought to send you off with.
I love a provocative thought. Let's hear it.
We've established that the paper treats noise as a crucial regularizing feature. It's not a mistake in the code. It is the vital entropy that smooths out systemic collapse and keeps the AI from getting stuck in an uncreative, meaningless singularity.
The system mathematically requires the chaos to function properly.
Exactly. So let's turn that lens on ourselves. If we look at human cognition, if our own brains also require a delicate biological balance of intense focus and scattered wandering mental noise, could this exact mathematical phase transition explain the human experience of epiphany?
Oh, wow.
Think about the sudden aha moment you experience when you are taking a shower or going for a walk. You are intensely focused. You have a scattered, noisy mind thinking about a dozen things at once.
Right. The noise is very high.
The noise is high. The uniform state feels globally minimizing. You are comfortable in your little crater of distraction. And then a slight shift in your internal coupling strength, a tiny subconscious change in attention, and bam, the degree 2 cortic obstruction hits your brain. The scattered noise instantly, discontinuously snaps into a sharp, singular insight. You solve a problem you weren't even actively trying to solve.
Are human epiphanies just discontinuous phase transitions in the high-dimensional sphere of our own consciousness?
That's what I'm asking.
That is a profound extrapolation. It suggests that the mathematics governing a transformer's artificial attention might just be the universal mathematics of insight itself. Whether it's digital tokens on a sphere or neurons in a biological brain, the physics of pulling order out of chaos might be completely identical.
From the murky, scattered noise of our opening to a mathematically perfect U-shape, or rather a quartic shape of an epiphany. That is the beauty of looking at the world through this lens.
It really is.
The code might be hidden in a black box, but the physics of the universe still apply, even inside the machine. Thanks for taking the plunge into the high-dimensional sphere with us today. Keep questioning the noise in your own life, keep balancing your attention, and we'll catch you on the next deep dive. Usually when we talk about medical diagnosis, there's this expectation of, well, precision.
Right, like an engineering problem.
Exactly. You break your arm, you go to the hospital, the x-ray shows that jagged white line on the screen, and the doctor just points a pen at it and says, there it is.
Yeah.
That's the problem.
It's binary. It's totally physical.
Broken or not broken, it's clean.
And, it's comforting, right? We like things to be visible, to be categorized. We are visual creatures, so when we can map a system out perfectly, we feel like we control it.
But then you step into the world of artificial intelligence. You step into deep learning, massive language models, the stuff running the modern world, and suddenly that x-ray machine is just, well, it's completely broken.
Oh, absolutely.
We're looking at a diagnostic landscape of how these neural networks actually learn, and honestly, it is murky. It's the ultimate black box. We see billions of parameters, we see thousands of layers of computer code, but the precise moment a model goes from spewing random, chaotic noise to actually understanding a concept.
Yeah, that exact transition is incredibly difficult to map.
It is the absolute definition of diagnostic muddy waters.
For a long time, we've just accepted that as the cost of doing business with neural networks. We feed the data in, we wait, magic happens, and intelligent text comes out. But today, we are going to attempt to clear that water, because the paper we are diving into does something that is, quite frankly, a monumental paradigm shift in how we understand AI.
Exactly. So welcome to you, our listener, to a very unprecedented deep dive. Today, we are executing what we're calling the unabridged protocol.
Yes.
We have a densely packed, incredibly complex mathematical paper sitting in front of us, and we are going to examine it strictly linearly.
Line by line.
Line by line, equation by equation, from the title all the way to the final author email address at the very end. No skipping, no jumping ahead.
And the mission here, why this actually matters to you listening, is that we are looking at the mathematical foundation of how AI models, specifically transformers, behave when you view them not as software, but as continuous physical systems of interacting particles.
Right. We are going to map the thermodynamics of artificial attention. And to do this properly, here are the protocol rules you'll hear today. After every single concept, every paragraph, every complex formula, we're going to do a strict completeness check.
Just to ensure no nuance is left behind.
Exactly. And every mathematical symbol will be spoken with absolute precision according to our audio-style math reading protocol. But before we even read the title, we need to lay some groundwork. We need a quick 5-minute explanation of what a phase transition actually is in this context, because the paper assumes you know this.
Right. So a phase transition, think about water turning to ice. That is the classic physical analogy, and it actually maps beautifully to what happens inside a neural network.
Okay, so water to ice.
Yeah. In physics, a phase transition is a sudden, macroscopic change in the state of an entire system as you tweak a single underlying parameter, and usually that parameter is temperature.
So if you have a glass of water sitting on a table at, say, 1 degree Celsius, it's a liquid. The water molecules are disordered. They're tumbling over each other, sliding past each other, totally uniform in their chaos.
Precisely. If you look at the density of those molecules, it is roughly uniform throughout the glass. Now, you lower the temperature of that room by just 2 degrees, down to -1 degree Celsius. For a moment, the water might stay liquid, but then suddenly, boom.
It freezes.
The entire geometry of the system snaps. It breaks that uniform symmetry and locks into a rigid, highly ordered crystal lattice. It becomes ice.
And what's wild is that the individual water molecules didn't change at all, right? They're still just H2O.
Right, the molecules are the same,
Yeah.
but the collective behavior of the billions of molecules underwent a massive structural shift just because the environment crossed a critical threshold.
So how does that apply to machine learning,
Mhm.
to a transformer?
Well, imagine the words, the tokens, in a transformer model. Before the model is trained, or if the background noise in the system is cranked up too high, these tokens are uniformly distributed across a high-dimensional space. They are like the liquid water, completely disordered, paying no meaningful attention to each other.
Just a uniform sphere of static.
Exactly. But as the model learns, or mathematically, as the interaction strength of the attention mechanism overcomes that background noise, it's the exact equivalent of lowering the temperature in that room.
The system cools down.
Yes. And the tokens clump together. They form clusters. The uniform state shatters and an ordered state emerges. This clustered state represents learned attention, moving from a disordered uniform state to an ordered clustered state. That is the phase transition we are hunting for.
Okay, that makes so much sense. So let's officially start the protocol and read the title verbatim. The title is Phase Transitions for the Noisy Transformer Model in Arbitrary Dimension.
Let's unpack that.
Yeah, I like to think of a noisy transformer model, like a massively bustling, incredibly chaotic cocktail party. Every token, every piece of a word is a guest at this party, and they are all trying to listen to each other over this intense background static.
A cocktail party in a space with thousands of dimensions, yes.
Right. The tokens are trying to align with each other, they are trying to cluster together, but the noise is constantly threatening to scatter them back into a crowd. And then we have in arbitrary dimension. What does that mean mathematically?
Well, previous work, including papers by these exact same authors, solved this problem, but only for a two-dimensional circle, which is relatively easy to map mathematically. It's just angles.
Just flat geometry.
Exactly. But real language models don't embed tokens on a 2D flat circle. They embed them in massive vector spaces with thousands of dimensions. By solving this for an arbitrary dimension, which means mathematically the variable can be any number greater than or equal to 2, the authors are proving that the geometry of this phase transition holds true no matter how incomprehensibly complex the vector space becomes.
Okay, that covers the title. Have we missed any nuances in the title before we move to the authors?
I think we've thoroughly unpacked the title. Let's proceed to the authors.
Great. The paper is authored by Kyunghoo and Matthew Rosenzweig. Acknowledging their incredible work here, let's move directly into the abstract. The first sentence of the abstract introduces the core engine of the paper. They state they studied the, and I quote, Makian-Vlasov free energy on the unit sphere associated with the unnormalized self-attention model.
Okay, we need a deep foundation here. We have to digress heavily into what a Makian-Vlasov equation is.
Yeah, because that sounds like 19th century physics, not modern AI.
It is. Back in the 1800s, physicists were trying to describe gases in a box. Trillions of interacting molecules. You can't write down Newton's laws of motion for every single molecule.
Right, the math is just impossible.
Exactly. So they moved to probability distributions. They said, we don't know where molecule 45 is, but we know the statistical likelihood of finding a molecule in this general area.
You track the crowd, not the person.
Right. But a Makian-Vlasov equation is a specific type of interacting particle system. It's used when the force exerted on one particle depends on the statistical distribution of all the particles combined. Think of a star in a galaxy. Your gravitational pull isn't just affected by the star next to you. You are being pulled by the collective mass of the entire Milky Way.
Or like a bird in a massive flock.
Exactly. So why use it for AI? Because instead of tracking individual tokens passing through discrete layers of a neural network, the authors zoom out to infinity. They treat the tokens as a continuous fluid of particles whose movements are dictated by the average behavior of the whole crowd.
Okay, that covers the first sentence of the abstract and the Makian-Vlasov foundation. Does that completely unpack the concept, or have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the abstract's equations.
All right, the abstract then drops the critical beta equation, the exact threshold where this phase transition occurs. We need to execute the pronunciation protocol for this.
I am ready. The equation for the critical inverse temperature is ID2 plus 1 beta D. the ratio of the modified Bessel function of the first kind of order d over 2 plus 1, evaluated at beta star of d, to the modified Bessel function of the first kind of order d over 2, evaluated at beta star of d equals 1 over d.
Okay, wait, I have to stop us here. What is a modified Bessel function of the first kind?
It is a dense term, I know.
Yeah, we were talking about word tokens, and suddenly we have Bessel functions. Let's get an intuitive explanation of this.
All right. To understand Bessel functions, think about vibrations. If you pluck a guitar string, the vibration is a simple one-dimensional math problem. You use simple sine and cosine waves, up, down, up, down.
Very straightforward.
But what happens if you hit a circular drumhead? The vibration isn't just back and forth, it ripples outward in 2D from the center, bouncing off the circular rim. To mathematically describe that, sine and cosine are no longer enough because the circular geometry forces the math to bend.
So you get a new math function.
Exactly. You get Bessel functions. They originate from solving differential equations on cylinders and spheres. They look like sine waves, but their amplitude decays as you move outward from the center, like ripples feeding in a pond.
Okay, but the abstract says modified Bessel function of the first kind.
Right. If you modify the differential equation, essentially swapping a plus sign for a minus sign, the oscillating ripple behavior disappears. Instead of rippling up and down, the function either grows smoothly or decays smoothly. These non-oscillating versions are the modified Bessel functions, and the first kind are the ones that grow exponentially as the input gets larger. They describe diffusion, like heat spreading on a circular plate, or, in our case, tokens jittering and diffusing on a spherical geometry due to noise.
And what about the order? The equation compares the function of order d over 2 plus 1 to the order d over 2.
The order signifies the complexity of the shape we are looking at on the sphere. Because we are working in an arbitrary dimension d, the order of the Bessel function scales with the dimension.
Okay, so the threshold is defined by these beautiful geometric ripples. Does that cover the critical beta equation from the abstract? Have we missed anything there?
I think we've fully unpacked the equation and the Bessel functions. Let's proceed to the abstract's dichotomy.
Right, the abstract then unpacks the phase transition itself. It states that if the inverse temperature beta is between 0 and beta star of d, the uniform density is the global minimizer and the transition is continuous. But if beta is greater than beta star of d, it's discontinuous.
We need to unpack what uniform density means physically for these token embeddings.
Yeah, what does that look like?
Well, beta is the inverse temperature. So if beta is small, the temperature is high, there's lots of noise. In this state, the token vectors are spread out perfectly evenly across the entire surface of the high-dimensional sphere. The neural network hasn't learned to differentiate anything. It's a state of total uniform ignorance.
White noise.
Yes. And if the temperature is high enough, the math says this uniform density is the global minimizer. It is the most stable state the system can be in. And if you slowly lower the temperature, the transition into a clustered state is continuous. It's a smooth, gradual fade-in of intelligence.
But if beta is greater than the threshold, if it's cold and the attention is strong, the abstract says it's discontinuous.
Right. The uniform state is no longer the global minimizer. The free energy landscape shifts dramatically, and instead of a smooth slide, the transition is a sudden, jarring jump into highly structured, dense clusters.
Okay, that covers the dichotomy presented in the abstract.
Yeah.
Have we missed any nuances in the abstract before we move to section 1?
No, I think we've thoroughly unpacked the abstract. Let's proceed to section 1, the introduction.
Awesome. Section 1, paragraph 1. The authors write about the transformer mechanism. They detail how self-attention updates a sequence of token representations by comparing queries and keys to form a probability distribution, which then weights the value vectors.
Yeah.
I want to connect this to everyday life. When you, the listener, use ChatGPT, this is exactly what is happening under the hood. Every word you type is a token, and the AI is constantly updating those tokens by comparing them to every other word to figure out the context.
And here is where the authors make a massive analytical leap. They take this discrete computer science process, layer 1, layer 2, layer 3, and they analyze its continuous time limit.
Turning discrete steps into a smooth flow.
Exactly. They model the self-attention mechanism as a gradient flow, a system of interacting particles moving continuously on the surface of a sphere, denoted as Zeta-null.
All right, that covers the first paragraph of the introduction. Have we missed any nuances there?
I think we've thoroughly unpacked the transformer mechanism setup. Let's proceed to equation 1.1.
Okay, equation 1.1 is the unnormalized self-attention drift. This dictates exactly how these particles move. Let's execute the pronunciation protocol.
The drift equation is xa dot I dot equals the orthogonal projection onto the tangent space at x day, applied to the quantity 1 over n times the sum from j equals 1 to n of e to the power of beta times the dot product of xi and xj times the vector xj.
Okay, we have to follow the y mandate here.
Yeah.
Why is that orthogonal projection, that Padot term, absolutely necessary in this equation?
Because without it, the model collapses. Literally. If you just have tokens pulling on each other with exponential force, they would all sink directly into the dead center of the sphere and merge into a single microscopic point.
They just fall off the surface of the globe.
Exactly. The orthogonal projection, mathematically defined as the identity matrix minus the outer product of the vector with itself, acts as the solid ground. It ruthlessly strips away any force that points directly inward or outward. It ensures the particles are geometrically constrained to slide only along the surface of the sphere.
It's the mathematical equivalent of layer normalization. Excellent. Does that cover equation 1.1 and the drift? Have we missed any nuances?
I think we've unpacked it. Let's proceed to equations 1.2 to 1.4.
These equations define the centered pair potential. They explore a function y beta and a normalizing constant beta. The authors explicitly state they are making the potential centered, meaning its integral over the sphere equals 0.
We need to explain why this is mathematically vital.
Yeah, because in physics, if you just add or subtract a constant energy to a whole system, it doesn't change how things move, right? A ball rolls down a hill the exact same way at sea level as it does on a plateau.
You are totally right. The physical velocity doesn't change at all. But this is mathematical housekeeping. Later in the paper, they are going to isolate microscopic perturbations. They are going to look at tiny ripples in the token density. If the potential isn't centered, the massive baseline energy of the uniform state will completely overwhelm and pollute those calculations.
Ah, I see. It zeroes out the scale so you can weigh the feather.
Exactly. Making the integral zero isolates the perturbations perfectly.
Okay, that covers the centered pair potential. Have we missed any nuances?
I think we've unpacked it. Let's proceed to paragraph 3.
Paragraph 3 is where they add noise. The authors introduce isotropic Brownian noise to the particle dynamics. So the obvious question, why add noise if we want the AI to be accurate? Isn't noise a flaw?
It sounds like a flaw, but it's the secret to generalization. Without noise, the attention mechanism is too greedy. The tokens would instantly clump into infinitely dense points, perfectly memorizing the training data, but they wouldn't understand broad patterns.
They'd overfit immediately.
Right. The Brownian noise regularizes the dynamics. It smooths out those small-scale collapses. It's a constant interplay between attractive attention pulling tokens together and noise pushing them apart. That tension is what creates functional intelligence.
Got it. Does that cover paragraph 3 and the introduction of noise? Any nuances missed?
I think we've unpacked the noise. Let's proceed to equations 1.5 to 1.7.
These equations formalize the free energy and the couplings. Time for the pronunciation protocol for the free energy equation 1.5.
The free energy equation is Fk beta k equal n to 1 test C1 is D1 times SD1 W1 times SD1 FC1 times beta F sub k comma beta of mu is defined as the relative entropy of mu with respect to sigma minus k times the double integral over the d minus 1 dimensional sphere cross itself of the centered potential W beta of x and y integrated with respect to the measures mu of x and mu of y.
You need a deep foundation on the first term there. Relative entropy. What does that actually measure in this context?
Relative entropy measures the cost of deviating from the uniform distribution. Remember, entropy wants chaos. It wants everything spread out uniformly, which is the measure sigma. If the particles try to cluster together, measure mu, the relative entropy calculates exactly how much thermodynamic penalty they pay for fighting the natural chaos of the universe.
So the total free energy is the chaos penalty minus the interaction reward.
Exactly.
All right, that covers the free energy equations. Have we missed any nuances?
I think we've fully unpacked the free energy. Let's proceed to theorem 1.1.
Theorem 1.1 is the main result of the paper. It's a line-by-line breakdown of the phase transition. It states that there exists a threshold beta-beta. For beta-beta, the critical coupling keta-beta equals the linear stability threshold, making the transition continuous. For beta-beta is strictly less than k-Tachman is, making it discontinuous.
And we need to emphasize the significance of that linear stability threshold, Taitav-Galerball. The authors prove that this threshold perfectly matches what they call the degree 1 threshold,
Meaning what exactly?
meaning that when the uniform state first starts to break under high temperature, it always breaks in the simplest possible geometric way, a degree 1 dipole, like a smooth slosh of data to one side of the sphere.
It doesn't shatter into complex patterns right away.
Right, and matching those thresholds mathematically guarantees the smooth, continuous nature of the transition in that regime.
Okay, that covers the main result. Theorem 1.1. Have we missed any nuances?
No, I think we've thoroughly unpacked the theorem. Let's proceed to remark 1.2.
Remark 1.2 is incredible. The authors talk about the Kuromoto model. They show equation 1.12, which demonstrates that for very small beta, the complex exponential attention math simplifies into a basic sine function.
Yes.
And I just have to use this analogy. The Kuromoto model is famous for explaining fireflies flashing in unison on a summer night. Thousands of fireflies start flashing randomly, total noise. But slowly, they pay attention to their neighbors, and suddenly the whole tree line is flashing together.
It's the mathematics of biological synchronization. And what's staggering here is that when you deconstruct equation 1.12, it shows that an advanced AI transformer model, when operating at a high temperature, is governed by the exact same differential equations that describe those synchronized fireflies or pendulum clocks ticking on a wall.
The attention mechanism mathematically collapses into the physics of natural synchronization. It's beautiful. Does that cover remark 1.2? Have we missed any nuances?
I think we've unpacked the Kuromoto connection. Let's proceed to equations 1.13 to 1.198.
These cover the quotients, numerical data, and asymptotics. The authors provide a numerical table, 1.15, showing data points for the threshold in different dimensions. Then they deconstruct a large doll expansion in 1.16 and a predicted behavior for large beta in 1.18.
We need to address the why mandate here. Why do the authors suddenly use a finite-dimensional Lyapunov-Schmidt or Landau expansion here?
Yeah, why switch mathematical tools?
Because for very large beta, the extremely cold, highly clustered regime, the exact equations become mathematically intractable. You can't solve them perfectly. So they use a Landau expansion to formally predict the thresholds by approximating the free energy landscape. It's a way to theoretically predict boundaries that are too hard to solve exactly right now.
Ah, so it's a very advanced mathematical estimation.
Yes, and their numerical tables back up the estimation perfectly.
Great. That covers equations 1.13 to 1.19 and finishes section 1. Have we missed any nuances before moving to section 2?
I think we've thoroughly unpacked the introduction. Let's proceed to section 2, the variational formulation.
Section 2 begins with paragraph 1 and equation 2.1, introducing spherical harmonics.
We need to take significant time here. We need a deep foundation on what spherical harmonics hell actually are.
Let's do it.
Think about a standard Fourier series. If you have a messy sound wave on an oscilloscope, a Fourier series breaks it down into simple sine and cosine waves. You extract the fundamental tone, the first harmonic, the second, and so on.
Right.
But a Fourier series only works on a flat line or a circle. What if your data lives on the curved surface of a sphere? If you wrap a flat grid of sine waves around a globe, it crunches up and distorts at the north and south poles. The math breaks.
Because of the poles. So you need native spherical math.
Exactly. Spherical harmonics are the perfect tool because they are the natural vibrations of a sphere. Degree 0 is just a constant uniform color. Degree 1 is a dipole, 1/2 positive, 1/2 negative. Degree 2 is a quadrupole 4 alternating sections. They allow the authors to break down any chaotic token distribution into a clean sum of independent geometric patterns.
That covers paragraph 1 and spherical harmonics. Have we missed any nuances?
I think we've unpacked the harmonics. Let's proceed to equations 2.2 to 2.3.
These equations introduce the Laplace-Beltrami operator. Time for the pronunciation protocol.
The eigenvalue equation is delta SD1 YIL, y minus the Laplace-Beltrami operator on the d minus one-dimensional sphere applied to y equals a sub L comma times y.
What exactly does that operator do?
It's essentially the spherical version of a second derivative. It measures the curvature or sharpness of a function on the sphere. The spherical harmonics are the natural eigenvectors of this operator, and they use a reproducing kernel, ZL, to project any function cleanly onto these harmonics.
Perfect. Does that cover the Laplace-Beltrami operator? Any nuances missed?
I think we've unpacked it. Let's proceed to equations 2.4 to 2.8.
These equations deconstruct the mathematical definition of relative entropy and establish a crucial gap identity for the free energy. They're essentially writing out the strict mathematical bounds for how the energy behaves when the tokens are near the uniform state.
Right, they're setting up the scaffolding to prove stability.
Okay, that covers the entropy gap identity. Have we missed any nuances?
I think we've unpacked the gap identity. Let's proceed to equations 2.9 to 2.10.
This is where it gets intense. They define the linear stability threshold. They introduce a normalized second variation, and they define a variable play. Lambda, lambda 1.
Yes.
Okay, push back for me here. So lambda is just a ratio of eigenvalues.
Yeah.
Why is the paper absolutely obsessed with whether this ratio is less than or equal to 1?
This is the degree 1 leading concept, and it is the heartbeat of the entire paper. Let's visualize the uniform token distribution as a perfectly round, fragile glass balloon. The eigenvalues, the lambdas, represent how hard the attention mechanism wants to squeeze that balloon into a specific shape.
Okay.
Lambda 1 is how hard it wants to squeeze it into a simple dipole.
Oh.
Lambda 2 is how hard it wants to squeeze it into a quadrupole. If Slangdol, which is the ratio of any higher lambda to lambda 1, is less than 1, it means lambda 1 is the strongest force.
The balloon wants to become a simple dipole more than anything else.
Exactly. And if that's true, the balloon just smoothly sloshes to one side. But if $20.2 is greater than 1, it means higher order perturbations, complex shapes overtake the simplest perturbation. The system doesn't slosh, it fractures in complicated ways. The smooth, continuous transition is destroyed.
The balloon crumples.
Yes.
That is brilliant. Does that cover equations 2.9 and 2.10 and the linear stability threshold? Have we missed any nuances?
I think we've unpacked the degree 1 leading concept. Let's proceed to definition 2.1 and lemma 2.2.
Here they formally define continuous versus discontinuous transitions based on the global minimizer M-barrel and its weak limits as the coupling dollar approaches the critical threshold.
And we need to step through the proof of lemma 2.2. The authors use terms like therefore and hence to build logical deductions. They prove that if a sequence of minimizers weakly converges to the uniform state, then the uniform state must be linearly stable. Hence, if it's not linearly stable, the transition must be discontinuous.
It's a rock-solid logical trap.
Precisely.
Okay, that covers definition 2.1 and lemma 2.2. Have we missed any nuances?
I think we've unpacked the transition definitions. Let's proceed to proposition 2.3.
Proposition 2.3 deals with critical point uniqueness. They break down the Kirkwood-Monroe equation, which is equation 2.16, and then they step through the proof from 2.18 to 2.22.
The Kirkwood-Monroe equation essentially characterizes the stationary points of the free energy, and we really need to highlight remark 2.4 here. The authors note an open uniqueness range between KC22 and $2.
What does that mean?
It means they strongly conjecture that the uniform state is the only critical point in that specific temperature range. But the mathematical tools don't exist to formally prove it yet. They prove local uniqueness, but global uniqueness in that gap remains an open problem in the field.
Fascinating. Okay, does that cover proposition 2.3 and the Kirkwood-Monroe equation? Have we missed any nuances?
I think we've fully unpacked section 2. Let's proceed to section 3, the Beckner on a free coercivity mechanism.
All right, section 3. Equations 3.1 to 3.2 introduce the Beckner weights. Let's execute the pronunciation protocol for the weight definition.
The Beckner weight equation is B sub L comma equals the gamma function of L times the gamma function of D divided by the gamma function of the quantity L plus D minus 1.
Okay, the gamma function. Briefly, for anyone who hasn't taken advanced calculus in a while, what is that?
It's essentially a continuous version of the factorial function. You know, 4 factorial is 4 times 3 times 2 times 1. But what if you wanted to know 3.5 factorial? The gamma function is an integral that smoothly connects the dots between integers, allowing you to calculate factorials for fractions and real numbers.
And here, they use it to create specific numerical weights for every single harmonic degree.
Exactly, a mathematical measuring stick for the vibrations.
Perfect. That covers the Beckner weights. Have we missed any nuances?
I think we've unpacked the weights. Let's proceed to proposition 3.1.
Proposition 3.1 is the dual Beckner-Onofre, or logarithmic Hardy-Littlewood-Sobolev inequality in equation 3.3.
We must fulfill the Y mandate here. This inequality is the actual engine of the entire paper. To prove a continuous transition, you have to mathematically prove that the chaos of the entropy is strictly greater than the pull of the interaction energy for every possible shape.
But you can't just calculate exact entropy for infinite chaotic particles.
Right. So Beckner's inequality acts as a bridge. It mathematically guarantees that the impossible to calculate relative entropy is always greater than or equal to a clean weighted sum of the spherical harmonic projections using those exact Beckner weights. It forces the entropy to overpower the interaction energy, ensuring the uniform state remains stable.
Wow. And they examine the equality case, the conformal Jacobians in equation 3.4, to show exactly when that inequality tightens. Does that cover proposition 3.1? Have we missed any nuances?
I think we've thoroughly unpacked the inequality. Let's proceed to lemma 3.3.
Lemma 3.3 covers endpoint uniqueness. They deconstruct the proof using Gegenbauer, or ultraspherical polynomials, in equations 3.0 to 3.13.
Yeah.
I like to think of Gegenbauer polynomials as a highly specialized measuring tape. If regular polynomials measure flat space, these polynomials are perfectly calibrated to measure distances and angles on the curved surface of higher dimensional spheres.
That is a great analogy. They use them to prove uniqueness at the absolute endpoint of the stability regime.
Awesome. Does that cover lemma 3.3? Have we missed any nuances?
I think we've unpacked it. Let's proceed to theorem 3.5.
Theorem 3.5 is the Beckner-Onofre continuity criterion. They step strictly through a massive proof from equation 3.18 to 3.31 using heat semigroup regularization.
We need to explain why heat kernel regularization, denoted as TPT delta, is used.
Yeah, why introduce heat to the math?
Because infinite sums in mathematics are extremely dangerous. If you try to manipulate them directly, they can blow up to infinity before you can evaluate them. Applying the heat semigroup is like running a mathematical blowtorch over the sharp edges of the probability distribution.
It smooths everything out.
Exactly. It forces the infinite sums to converge absolutely. They put on their safety goggles, do the dangerous math to prove the stability inequality, and then they take the limit as the time goes back to zero. The smoothing vanishes, and the rigid proof remains.
That is incredibly clever. That covers theorem 3.5 and finishes section 3. Have we missed any nuances?
I think we've thoroughly unpacked the coercivity mechanism. Let's proceed to section 4, the noisy transformer coefficients.
Section 4 connects the abstract math back to the actual AI model. Lemma 4.1 calculates the Funkek coefficients. They deconstruct the eigenvalue formula for the attention kernel in equations 4.1 to 4.3.
And they find that the eigenvalues for the transformer's exponential attention are exactly proportional to those modified Bessel functions we discussed at the very beginning. The abstract geometry maps perfectly to the physical wave equation.
The loop closes. Okay, that covers Lemma 4.1. Have we missed any nuances?
I think we've unpacked the coefficients. Let's proceed to lemma 4.3.
Lemma 4.3 is the Bessel ratio comparison. They analyze the strict monotonicity property and elementary bounds in equations 4.7 to 4.10. Then they step through a massive proof using mathematician Javier Segura's results on modified Bessel functions and continued fractions from equation 4.13 to 4.21.
This is crucial. By using continued fractions, they prove that the Bessel ratios naturally decay as the harmonic order increases. They prove that you can multiply adjacent ratios together.
Which means what exactly?
It means the degree 2 ratio, the quadrupole vibration, acts as a shield. If they can prove that the degree 2 ratio stays below its Beckner weight of $1, then the mathematics force all the higher frequencies, degree 3, 4, infinity, to be even smaller. If the degree 2 shield holds, the entire infinite tower of higher vibrations is perfectly safe, satisfying the Beckner-Onofre criterion.
So the whole continuous learning theory rests on the shoulders of degree 2.
Precisely.
Amazing. Does that cover Lemma 4.3? Have we missed any nuances before moving to section 5?
I think we've unpacked the Bessel ratios. Let's proceed to section 5, the degree 2 quartic obstruction.
The dark side of the threshold. Lemma 5.1 details the obstruction. And just realizing this, if $20, the degree 2 shield breaks, and the whole continuous transition theory breaks down.
Exactly. If we push the temperature so low that the ratio creeps above 10 $, the interaction energy inside the quadrupole shape becomes stronger than the entropy.
So how do they prove the system shatters?
They walk through a proof using a specific perturbation in equation 5.4. 12 epsilon, 1 most epsilon varphi plus epsilon 2.
What are those terms? One is the uniform state. Epsilon varphi is a tiny degree, 1 dipole nudge, and epsilon dollars is a squared degree 2 quadrupole nudge.
Yes, they deliberately mix a dipole wobble with a squared quadrupole wobble. Why? Because right at the critical boundary, the first order forces are perfectly balanced. The quadratic terms, the epsilon 2 terms of the entropy and interaction, perfectly cancel each other out.
It's like balancing a pencil on its tip.
Exactly. The net force is 0. So to see if the pencil falls, they have to dig deeper. They break down the Taylor expansion of the free energy to the fourth order in equations 5.5 to 5.7. Because the epsilon 2 terms perfectly cancel, the system's fate relies entirely on the epsilon 4 terms, the quartic terms.
The quartic obstruction.
Yes, and they prove in equation $5.10 that if 2 is silently dollars, the coefficient in front of that quartic term becomes strictly negative.
And a negative free energy means the system violently wants to go there.
The uniform state is no longer a global minimizer.
Hmm.
The system falls down this invisible quartic pathway and snaps discontinuously into a dense clustered state.
The Boolean crumples. Okay, does that cover lemma 5.1 and section 5?
Yeah.
We missed any nuances.
I think we've completely unpacked the quartic obstruction. Let's proceed to section 6.
Section 6 is assembling the pieces, proving the main result. They trace the final logical steps. They combine the eigenvalues from lemma 4.1, the shielding property of the Bessel ratios from lemma 4.3, the continuous heat semigroup engine from theorem 3.5, and the shattering of the shield in lemma 5.1.
They perfectly bind all the mathematical theorems together to finally formally prove theorem 1.1. If you are below the threshold, you slide smoothly into intelligence. If you cross it, you snap discontinuously.
Staggering. That covers the assembly in section 6. Have we missed any nuances?
I think we've assembled the proof completely. Let's proceed to the final step, the references and affiliations.
As per the strict linear unabridged protocol, we must read the final text lines exactly. I will begin. Kyunghoo, Department of Mathematical Sciences, Carnegie Mellon University. Email kmuman@andrew.cu.edu.
Matthew Rosenzweig, Department of Mathematical Sciences, Carnegie Mellon University. Email.rosens2@andrew.cmu.edu.
And that covers the final text of the document. Have we missed any nuances in the affiliations?
The protocol is complete. No nuances missed.
Incredible. We waded through the muddy waters and executed the protocol. But before we sign off, I want to pull back. We spent this entire time talking about ideal math, infinite dimensions, spheres, heat semigroups. But what does this all mean for the big picture, for the reality of AI today?
Well, I'll leave you with this final provocative thought. We just spent hours breaking down how noise and attention battle it out on an idealized mathematical sphere. But think about what this implies for the massive servers running AI right now.
Right. Companies are spending billions of dollars on compute power just throwing raw electricity at the problem.
Exactly. But if these phase transitions govern the physical geometry of data, could future neural networks be designed not as discrete layers of code to be brute forced, but as physical thermodynamic systems? What if we could build hardware where we simply lower the temperature of the data environment and force the data to naturally crystallize into intelligence?
Just like water freezing into ice.
Yeah.
Added a wild thought. It's not just a cocktail party anymore. It's a phase change of information itself. We're moving from software engineering to literal data physics.
Absolutely.
Well, to you, our listener, thank you. Thank you for surviving the unabridged protocol, for wading into the diagnostic muddy waters with us, and for exploring the geometry of artificial minds. You've successfully completed this deep dive.
Welcome back to The Explainer. Today we're looking at something literally mind-bending. Usually when we talk about artificial intelligence, we're talking about code, massive server farms, and data sets. The usual stuff. But today we're diving into a groundbreaking paper by Kyunghoo and Matthew Rosenzweig called Phase Transitions for the Noisy Transformer Model in Arbitrary Dimension. And guys, this paper does something absolutely incredible. It takes the inner workings of modern AI and proves that its attention mechanism actually mathematically mirrors the laws of particle physics. It's this stunning bridge between theoretical math, physics, and machine learning. Okay, so here's our roadmap for today's explainer. First, we'll go inside the transformer model. Then, we'll visualize tokens as spherical particles, look at the battle between attention and Brownian noise, and find the mathematical tipping point. After that, we'll break down continuous versus discontinuous transitions, and finally, scale it all up to the multidimensional AI universe. Okay, let's dive into this. Section 1. Inside the transformer model, moving beyond code. So when we picture large language models, we almost always imagine massive walls of Python code, right? But recently, mathematicians have started isolating the self-attention mechanism, which is really the beating heart of the transformer, and they're looking at it as a continuous time dynamical system. They are essentially stripping away the computer science entirely and treating the AI like a physical environment. And that brings us to a super fascinating question I want you to keep in the back of your mind today. What if AI attention acts like gravity? What if the words and concepts inside a neural network aren't just data points, but actual objects exerting physical forces on one another?
Well, to study this, the authors focus on a mathematical sandbox known as the Unnormalized Self-Attention, or USA model. In simple terms, this is a stripped-down AI architecture where the attention mechanism acts as an isotropic spherical interaction among tokens. Now, don't let the jargon scare you off. Isotropic literally just means it behaves exactly the same in all directions. So this gives mathematicians a perfectly clean, perfectly symmetrical space to study exactly how these tokens interact and influence each other.
Section 2. Tokens as spherical particles, the geometry of language. To really wrap our heads around this, we have to completely change how we visualize a sentence. You see, after a process called layer normalization, token embeddings, which are essentially the AI's mathematical understanding of words or chunks of data, are modeled as directions, or tiny physical particles existing on the surface of a multidimensional unit sphere. So we're not looking at flat lines of text on a page anymore. Instead, I want you to imagine a massive glowing globe, where every single word is a distinct planet or particle moving across its surface. Section 3. Attention versus Brownian noise, the battle for structure. Inside this mathematical sphere, there's a battle going on. There are two competing physical forces fighting for control over our particles. On one side, we have self-attention. This acts just like gravity. It desperately wants to pull related tokens together, clustering them into meaningful concepts. But on the exact opposite side, we have Brownian noise. Think of this force like heat or scattering energy. It pushes the tokens apart, constantly trying to spread them out evenly across the sphere in a state of absolute uniformity. It perfectly illustrates the delicate balancing act happening inside an AI every single time it generates a word. The authors actually put it beautifully in the paper. They wrote, "At the modeling level, this noise can be viewed as unresolved layer-wise variability. At the variational level, it regularizes the attractive attention dynamics and smooth small-scale collapse mechanisms." So what does that mean in plain English? Basically, noise is not a bug. If the gravity of the attention mechanism was too strong, all the words would just collapse into a single point, like a black hole of totally useless data. The noise is an absolutely crucial physical force that prevents this collapse, keeping the whole system healthy and dynamic. Section 4. The mathematical tipping point, when chaos becomes order. Now we arrive at the absolute climax of Munn and Rosenzweig's research. To find the exact tipping point between these forces, the authors use a concept straight from physics called the free energy formula. The system is always naturally seeking to minimize its free energy, which you calculate by taking the entropy, so the chaos or the noise, and subtracting the interaction energy, which is that clustering force of attention. The AI model is just constantly trying to find the lowest possible energy state between these two competing forces. And this creates what mathematicians call the phase transition problem. The entire goal of this paper is to find the exact critical coupling strength, the precise temperature or noise level where that uniform density finally breaks down. Putting that into AI terms, this is the exact microsecond the AI stops being a scattered cloud of random noise and suddenly snaps into focus, grouping words together to form a coherent thought. Section 5. Continuous versus discontinuous transitions, the nature of the snap. So how exactly does that snap happen? Well, to prove the mechanics of this transition, the authors utilized some incredibly dense, beautiful mathematics. They used these sharp Beckner-Onufried inequalities to measure energy on the sphere. They computed Funkeke coefficients using modified Bessel functions. I know, it's a lot. We absolutely don't need to get bogged down in the heavy calculus today. But the crucial takeaway from all this rigorous math is that they identified a unique threshold, denoted as beta star based on inverse temperature. In what they proved is a strict dichotomy. If the inverse temperature is below that unique threshold, the AI organizes itself through a continuous transition. It's a smooth, gradual shift from chaos into order. But, and here's the wild part, if the inverse temperature is above that threshold, the math dictates a discontinuous transition. Global minimality is lost strictly before linear stability. In plain terms, the system undergoes an abrupt, violent snap right into structure. Just by tweaking the background noise, the fundamental physical nature of how the AI thinks completely changes. Section 6. The multidimensional AI universe. Scaling up the sphere. Up until now, a lot of this theoretical math had only ever been solved for two-dimensional circles. But as we know, real neural networks do not operate in 2D. They operate in hundreds, sometimes thousands of dimensions. The authors actually tracked this critical threshold, that beta star tipping point we were just talking about, across these different dimensions. If you look at the numbers, notice how in dimension 2, the threshold is roughly 2.44. But as you scale up to a 10-dimensional sphere, the threshold smoothly decreases down to about 1.21. The truly monumental achievement of this paper is proving that this global minimizer dichotomy holds true in arbitrary dimensions. It doesn't matter if the AI is operating in 3 dimensions or 3,000 dimensions. The fundamental mathematical laws of this phase transition remain entirely intact. This completely bridges the gap between highly theoretical mathematics and real-world AI engineering. Which leaves us with this final provocative thought for today. As we build AI systems that are larger and more complex, we're really no longer just writing code. We are simulating physical universes. If the attention mechanism inside an AI perfectly mirrors the phase transitions of particle physics, how will the mathematical laws of the universe dictate the architecture of our next generation of large language models? It's a question that completely blurs the line between computer science and physics, and I honestly can't wait to see where it leads us. Thanks so much for joining me on this explainer, and keep exploring.
Welcome to the Explainer. Today, we're doing something a little bit different. We're going to look under the hood of arguably the most powerful technology of our time. But we're going to do it through a completely unexpected lens. We're going to uncover the hidden physics operating right inside modern artificial intelligence. We're digging into a seriously fascinating new paper by Kyunghoo and Matthew Rosenzweig. It's titled Phase Transitions for the Noisy Transformer Model in Arbitrary Dimension. And honestly, it turns out that the way AI models process language looks a whole lot like the literal laws of thermodynamics.
Okay, let's quickly run through our roadmap for today. We're going to cover tokens as physical particles, attention versus random noise, the phase transition threshold, how dimensionality changes the math, the mathematical toolkit, and finally, why these proofs actually matter.
All right, let's kick things off with Section 1, Tokens as Physical Particles, Mapping AI to a Sphere.
To really get this, we've got to completely shift our perspective for a minute. When you type a prompt into an AI, you probably imagine, lines of code processing your words. But mathematically, we actually need to visualize a physical geometric space. By viewing tokens, which are basically pieces of words or concepts, as directions on a sphere, this paper models the AI's attention update as an interacting particle system. Literally, think of a globe. Every single token is a tiny particle resting somewhere on the surface of this sphere. This is what's known as unnormalized self-attention, and it is just a brilliant way to visualize what is actually happening under the hood of a neural network. Instead of abstract data processing, we're suddenly looking at a dynamic, physical environment. It's really cool.
Moving right along to Section 2, Attention versus Random Noise, the forces at play. So now we've got our little token particles sitting on the sphere. But they aren't just chilling there. We have to introduce the core conflict. There are two competing forces fighting for dominance here. On one side, we have the self-attention mechanism itself. Attention acts exactly like gravity, pulling token particles together based on how relevant they are to each other, forming these really tight clusters. But on the other side, we have random noise, represented here as a sort of Brownian motion or heat. This noise acts to push the particles apart, spreading them uniformly across the whole sphere. So it's a constant tug of war. You have gravity pulling things in and heat pushing things out. And here is where it gets absolutely fascinating. When the balance between these two forces tips at a very specific mathematical threshold, the entire system literally snaps. Physicists refer to this exact moment as a phase transition. Think of water turning to ice, right? It doesn't happen gradually, it happens the exact moment the temperature hits freezing. In our AI model, there is a critical point where the heat can no longer overpower the gravity, and those evenly spread tokens suddenly collapse into clusters. The researchers modeled this snap using something called the McKean-Vlasov free energy equation.
Which brings us nicely to Section 3, the Phase Transition Threshold, breaking down Theorem 1.1.
So the real meat of this paper is their main result, Theorem 1.1. This pinpoints exactly when the snapping occurs, and not just in our standard 3D world, but in any geometric dimension. This theorem proves that there is a strict dichotomy. Below the threshold, in what they call the continuous regime, the noise wins out and uniform spread is the only stable state. But above the threshold, in the discontinuous regime, that uniformity totally shatters and clustering takes over. And the researchers didn't just theorize this might happen. They found a unique mathematical equation that solves for this exact boundary point, identifying the literal split second the transition snaps.
Okay, section 4. Dimensionality changes the math, and guys, this is the twist in the tale.
Right. So here's the twist the authors introduce regarding the dimensionality of our geometric sphere. And it kind of changes everything we thought we knew about this phase transition. If we map these tokens onto spheres with more and more dimensions, so going from a 2D circle to a 3D sphere to a 4D hypersphere and way beyond, how does that change the physical snapping point? Basically, does it take more gravity to pull the tokens together in higher dimensions or less?
Take a look at these numbers. There is a super clear, strict decreasing trend happening as the dimensions increase. In dimension 2, the critical threshold is around 2.44, but as you move down to dimension 3, 4, and 5, the threshold steadily drops. In higher dimensions, it actually takes less attractive force to trigger the sudden collapse of the tokens into clusters. It's wild. By the time we hit 10 dimensions, the threshold drops down to exactly 1.210397. I mean, think about that. This incredibly specific number anchors this highly abstract theoretical physics concept into a very concrete, measurable mathematical reality. It proves without a doubt that the geometry of the AI architecture fundamentally dictates its physical behavior.
Let's jump right into section 5, the mathematical toolkit, the engine of the proof.
Now, to actually prove these super precise numbers across arbitrary dimensions, the authors had to deploy some serious mathematical firepower. You don't just get exact thresholds in multidimensional space by guessing, right? Without getting completely lost in the equations, you can think of these advanced harmonic analysis tools as the intricate engine that allows them to prove this theorem with absolute ironclad mathematical certainty. They used sharp Beckner-Onofre inequalities to measure entropy on the sphere, Funk-Heck formulas to calculate how the forces interact, and this really clever degree 2 quartic obstruction to prove exactly when the uniform spread loses its stability. Honestly, it's a masterclass in applying high-level physics and math to computer science. And that brings us to our final section, section 6, why these proofs matter, bringing it back to AI.
Okay, so we've been geeking out over abstract math. We've talked about spheres in 10 dimensions, and we've mapped out these physical metaphors. But so what? Why does this McKean velocity free energy and these complex thresholds actually matter to the machine learning practitioners out there building the next generation of AI? Well, grasping these thresholds is absolutely essential because it helps us understand the fundamental physical limits and the stability boundaries of the powerful transformer architectures driving AI today. By knowing exactly when tokens will snap into clusters, engineers can perfectly predict how an AI will behave, how to balance the noise in the system to prevent total instability, and ultimately how to build models that are vastly more robust, efficient, and reliable. It literally takes the guesswork out of the architecture. So I want to leave you with a thought to chew on as we wrap up this explainer. If something as staggeringly complex as language processing and self-attention is, at its core, really just particles following the laws of thermodynamics on a sphere, what other hidden laws of physics are governing the neural networks of tomorrow? Understanding the math behind the machine is the absolute first step to unlocking its true potential. Thanks so much for joining me on this explainer, and keep questioning the physics of the digital world around you. All right. Let's just dive right into this explainer. Welcome, everyone. Today, we're unpacking a genuinely brilliant piece of mathematical analysis by Kyunghoo Moon and Matthew Rosenzweig. If you've ever found yourself wondering what actually happens inside an AI transformer model when you strip away all the complex coding and just boil it down to its pure, fundamental mechanics, well, you're absolutely going to love this. We're looking at how the authors brilliantly frame transformer attention mechanisms, not just as lines of code or algorithms, but literally as interacting physical particles governed by the laws of physics. It's a total paradigm shift. So, here's our roadmap for today. We'll start by looking at tokens as spherical particles, then introduce the concept of the noisy transformer.
From there, we'll pinpoint the exact phase transition, compare continuous and discontinuous shifts, and finally, look at how they solve this for arbitrary dimensions. Let's get to it.
Section 1. Tokens as spherical particles. Okay, so in deep learning, after the standard layer normalization process, you can essentially visualize data tokens as tiny dots interacting on the surface of a high-dimensional globe. Now, the absolutely crucial thing here is how these dots actually interact with one another. The authors focus on a simplified architecture they call unnormalized self-attention, or USA for short. Under this specific model, the system acts exactly like an attractive particle system. The tokens update themselves by comparing their query key inner products and aggregating their vectors. In plain English, they magnetically pull toward each other. And in a mean field limit, when you have a massive number of tokens, this attractive pull is rigorously described by the Minkowski-Vlasov equation. It's literally a gravitational-like system of data. How cool is that?
Moving right along to Section 2, introducing the noisy transformer.
Now, I want you to really think about this for a second. What happens when unresolved, purely random layer-wise variability is injected directly into this perfectly attractive attention mechanism? I mean, if the tokens are all desperately trying to pull together into a single dense point, what does throwing chaotic Brownian noise into the mix actually do to the entire system?
Well, adding this noise serves a really vital twofold purpose. Practically speaking, it mimics the actual unresolved variability that we see in real-world neural networks. But mathematically, it acts as a much-needed regularizer. It smooths out those small-scale collapse mechanisms, essentially stopping the tokens from just instantly clumping together into a useless singular point. And this creates a wildly fascinating stationary variational problem. Think of it as a literal tug-of-war. You have this intense competitive tension balancing the sheer chaotic entropy of the noise on one hand against the highly structured interaction of the attention mechanism on the other.
Which brings us to Section 3, finding the phase transition.
And this right here is where we see that order from chaos arc perfectly illustrated. The authors pinpointed what they call a strict global minimizer dichotomy. Imagine the uniform density of tokens as a gas spread perfectly, evenly over the surface of a balloon, right? That is the state of maximum chaos. But the moment the coupling interactions, that attractive attention force we talked about, surpass a specific noise threshold, well, that uniform density abruptly ceases to be the global minimizer of the system's free energy. Basically, in an instant, the gas suddenly clumps together into these highly structured, ordered clusters. It's a literal phase transition.
So you're probably asking, what is that exact threshold? Well, the authors discovered a unique inverse temperature threshold, which they denote mathematically as beta star. This precise tipping point is determined by an incredibly elegant ratio of modified Bessel functions of the first kind, specifically the function I sub d over 2 plus 1 divided by I sub d over 2, and they found that this ratio exactly equals 1 over d, where d represents the number of dimensions. This single beautiful equation dictates exactly when the transformer snaps from complete chaos into structured order.
All right, Section 4, continuous versus discontinuous shifts.
It is so important to carefully contrast these two different regimes. If you look at the left side of our slide, when our parameter beta is strictly less than or equal to that critical threshold, beta star, the transition is completely smooth. The uniform density remains the unique global minimizer right up to the linear stability threshold. So it's a continuous, graceful shift into order. But look at the right side. When beta is greater than beta star, things get, well, wild. Global minimality is lost strictly before reaching linear stability. What does that mean? It means the transition is discontinuous. A secondary clustered state essentially ambushes and overtakes the uniform state abruptly, causing this sudden dramatic snap in the system's underlying structure.
Finally, Section 5, solving for arbitrary dimensions.
Let's walk through this exact data together, pulled straight from their paper. We're looking at the number of dimensions, d, compared against that critical threshold we talked about, beta star. Look at the clear pattern emerging here as we go down the table. As the number of dimensions increases from 2 all the way up to 10, the critical threshold strictly decreases. It drops from 2.446 right down to 1.210. This reveals a really profound truth about the geometry of the system. Basically, the higher the dimension your AI tokens live in, the less interaction force is actually required to overpower the noise and trigger that phase transition into order. It's so counterintuitive at first glance, but the math completely proves it.
Now, I know some of our mathematically inclined viewers are wondering, how on earth did they prove this across literally any dimension greater than 2? Well, here are the heavy-hitting analytical tools they deployed. They utilized the sharp Beckner-Onofre inequality,
specifically the logarithmic Hardy-Littlewood Sobolev inequality on the sphere, to rigidly prove the continuous side of the transition. And as for the discontinuous side, they discovered what's known as a degree 2 quartic obstruction. This proved that a very specific mathematical perturbation abruptly lowers the free energy. It is genuinely masterful mathematical detective work.
I want to leave you with this final, incredibly provocative thought taken straight from the paper's introduction. The authors state that in a specific mathematical limit, the small beta limit, the attention interaction inside this AI model perfectly mirrors the classical synchronization model on a circle. Specifically, it converges to the identical oscillator Kuramoto model. Why does that matter? Well, because the Kuramoto model is the exact same classical physics mathematics used to describe how fireflies flash in perfect unison or how pendulum clocks eventually synchronize on a wall. It really forces us to ask, as we build these increasingly complex, cutting-edge AI transformers, are we simply recreating the fundamental, beautiful laws of physics that already govern the natural world? It is a mesmerizing thought to end on. Thanks so much for joining me for this explainer, and keep exploring.